Hey, my dear NEET and JEE NCERT warriors of class 12, the final day just before the exam has finally arrived, and it's time for the complete revision. And just like Shreyas Sir promised, Shreyas Sir has traveled thousands of kilometers just for you so that I can take this class in the studio. So, without wasting more time, let's quickly get into the session because I'm going to cover the summary and the points to ponder of all the chapters of class 12 physics NCERT in this particular session. Usually people don't look at summary and points to pointer, and there are many interesting things to learn there. Questions do come from these two things, and if you have missed reading or understanding these things, let's get to the task. Not just that, I feel that you can revise the entire physics of class 12 using these summary and the points to pointer, and it is a very effective way to revise, and not many people have done that on YouTube, right? So this is the session, one and only session that you will need, and make sure that you support this #1 English channel throughout the country, and not just that, the #1 favorite channel of majority of the students in South of India and Northeast India, and also obviously outside India. So thank you so much for your lovely support and your massive in the terms of likes, in the terms of comments, and in the terms of word of mouth, that you talk good about the channel as well as the teachers here. Yes, so let's begin with the class, and I hope I'm audible and visible perfectly. Let me know. Yes, looks like I am visible, and the session won't be very long, but yes, the session won't be very short also. The reason why I want to conduct this session is to make you confident, to make you see all the hidden things which might come in tomorrow's board examination. So let's begin with the lecture, okay? And let me tell you all the important problems. So in the Telegram group, I don't know how many of you have seen the Telegram group. Please join the Telegram group. I have given all the important questions from NCERT. All the important questions from NCERT, I have already given that to you. I have given you all the graphs which are there, in complete 12th standard. I have given you a session on derivations. If you have not watched it, please watch that. It is going to be very helpful, will give you a lot of marks. I have given you a complete session, right, on the question practice, the questions and the back exercise PYQ, and the most important questions. I have given you mock tests. The links are there in the description box. In fact, 3 mock tests I have given to all of you. The links are there in the description box, and many more things that I have been giving you regarding terms of strategy and the important things and do's and don'ts. So I hope you have been following this channel, right? So if you have not watched any of these classes, if you still have time, you still want some confidence, please watch those videos. Please download those resources. Links are there in the description box as well as in the Telegram channel. So make sure you're a part of it. All right. So let's begin. And by the way, let me tell you, after the board examination, your competitive preparation will start for your JEE, NEET, CUET, BITSTAT, you name it. All these exam preparations are going to go on in full swing. So there is no time to rest. You don't have to look at any other channel. You just have to subscribe to this channel. So make sure you do that. So let's start with chapter #1. Okay, let's look at the summary pointers and let's look at each point properly in detail, my dear warriors. Okay, so with me, everyone, with me. Okay, so let's have a look. And yeah, I don't want this. Okay, great. Why is it opened here? 1 second. Can I exit this? Yeah. No. Okay. This I want to open with Adobe. Okay. So let's open this up. Yep. Perfect. I don't want this. I want this, and I want to draw. I want to draw with 4PT. Okay. Perfect. Great. So let's quickly go to the required page. No, okay, just 1 second, guys. It's going to act little bit crazy. Just 1 second. Why is it not going? How do I go down? How do I go down? Okay, I'll go down like this, hopefully. Yeah, there you go. Okay, yes, so let's begin. My goodness. Yes. Okay, so starting off with the first point in summary, I hope I'm audible, visible properly. Hello, my dear students. I'm so sorry. It took a little bit of time because I'm not so used to Adobe Acrobat. I'm used to the Notes app. Electric and magnetic forces determine the properties of atom, molecules, and bulk matter. So that's one of the first pointers. See, that is kind of making sense also, because all the chemical properties, the color, how it will react, whether it will bond properly, what is the shape, what is the texture, how these molecules bind with each other, are completely based on the electromagnetic forces within the atom and the molecules. Perfect. From experiments on frictional electricity, one can infer that there are two types of charges in nature, and that like charges repel and unlike charges attract. By convention, the charges on the glass rod rubbed with silk is positive, which and that on the plastic rod rubbed with fur is then termed as negative. So people found out that whenever you rub things, then the charges go from one to the other and they develop opposite charge. If the charges go from one side to the other, if this is one type, this is the other kind, and there are only two kinds, and one is positive, one is negative. Who decided this is positive and negative? That is completely by convention, by history. One could have easily called the electron's charge as positive. One could have told the nucleus's charge positive. So if one would name electron's charge as positive, you would have questioned why is it like that. So it is just historical. So let's just assume that the charges on the nucleus is positive, the charges on the electrons are negative. That is purely historical reasons. All right. Then, my dear students, conductors allow the movement of the electric charges through them, and insulators will not allow any kind of movement. Whereas in metals, the mobile charges are electrons. In electrolytes, both positive and negative ions are mobile. This is a very important line over here. Conductors, yes, definitely, they have free electrons. Like if you are in your house and you ask permission to go out, chill out with your friends, your parents may not allow you. You are not free. But maybe your elder brother or sister is free to go wherever, because they don't have exams. They don't have anything to worry about. So that is the meaning of free electron inside an atom. Atom is like the house, the electrons are like you guys. So some electrons are free, just like your elder brothers and sisters who can chill out without exams. So they participate in the conduction of electricity. Whereas in electrolytes, it is not just the electrons which participate, the cations and the anions, the negative charges and the positive charges, both are involved. Remember, in conductors like copper, silver, aluminium, gold, etc., the nucleus stays there as it is intact, it is immobile. It's only the electrons which are responsible for, the conduction of electricity. Everybody with me? Yep, very good. Next, electric charges. Electric charges has three basic properties. This can come. Write down the properties of electric charges. Remember them: quantization, addition, and conservation. Quantization means that the charges are always multiples of electron charge, which is the basic charge, which is 1.6 10 to the power minus 19 coulombs, and you cannot go smaller than that. The second one is addition. That means when you say addition of charges, means that the total charge on a body is just the sum of the charges with the signs into account. Like 2 coulomb and 3 coulomb will give you 5 coulomb. 3 coulomb and negative 2 coulomb will give you 3 minus 2, which is 1 coulomb. So the sign is also important. That is why mention the line or the phrase algebraic sum. If you don't mention algebraic sum, you might lose marks on that. So make sure you put up the word algebraic sum. Is that clear, my dear warriors? Yes, very good, very good. Excelente. Moving on to the next part. Yep. The third one is conservation of charges, meaning that the charge on an isolated system totally is going to remain constant. Even if you rub them, if you exchange the charges, you charge it by some external means. If it is isolated, meaning nothing can go inside of it or outside of it, then the total charge will remain conserved. That is one of the important properties. So the total charge will remain conserved, and the charges can be transferred by friction, via battery, via some other electrical methods. Remember that whenever charge is transferred from one part of the body to the other part, or from one body to the other body, even the mass gets transferred. Yes, electrons do have certain mass, so the body which gets negatively charged will have slightly higher mass. The body which gets positive charge will lower down its mass. The mass will become slightly lesser. Do you understand why? Yep. Hello Navya. Hello everyone. Hello Kim. Hello Bhagyashri. Hello Rishi. Hello MN. Hello Hari. Nice to see all of you joining in live. Next, Coulomb's law states that the force of electrostatic attraction or repulsion is k q1 q2 by r square, and in vector form you put a unit vector over here. As simple as that. The Coulomb's constant is 1 by 4 pi epsilon naught, where epsilon naught value is 8.85. Remember this value, and k value is 9 into 10 to the power 9. All these are in SI units. In CGS, the value of k, etc. will change obviously. The ratio of the force of electrostatics upon gravity between an electron and a proton comes out to be this huge number, which suggests that electric force is much stronger than the gravitational force. And this is true for short distance. So if you take a proton and an electron at a very short distance, neglect the gm1 m2 by r square force, is the electric force which dominates like heavily, because 10 to the power 39 is so many number of times more than the gravitational force. So gravity is negligible. But when you compare Earth, Moon, Sun, etc., then the electric forces do not play a significant role. It's the gravitational pull which plays a significant role. Superposition. What is this superposition? Your mom says something, your teacher says something, your friend says something, you end up listening to every one of them. So electric charges are also exactly like that. Whatever the mom said, okay, I will do it. Whatever teacher says, I will do it. Whatever my friend said, I will do it. So everybody's effect is combined together to produce a net effect. So the principle is based on the property that the forces with which two people attract or repel each other are not affected by the third person, and the net force is basically the vector sum of all the forces acting on it. Like Pandu loves Champa, Champa loves Pandu. Alright, whatever happens between them is between them. Pandu's mom told, don't do this, he will listen. Champa told, do this, Pandu will listen. Teacher of Pandu said, do this and do not do that, Pandu will listen. So, Pandu listens to everyone, and whatever is the relation between Pandu Champa is not affected. So, two charges attracting or repelling is not affected by the third charge. In fact, the third charge will also apply the force. Fourth charge will also apply the force. All the charges together will apply the net force by vector addition. That's all. Electric field at any point is nothing but at a point is due to a charge configuration on a small positive test charge at a point divided by the magnitude of the charge, and the field is given by q by 4 pi epsilon naught r square. So when there is a charge and you want to know whether there is field around it, you test it. Like when your mom is making rasam or sambar or dal, doesn't she do, or dad is making some nice dish, haven't you seen your parents licking that food little bit, and they're like, okay, the salt is less, or the masala is less, or that is more, that is less. Same way, whenever you have to test the field, what you do, you use a test charge. The test charge experiences a force, and you divide the force by the charge which you are testing, on which you are testing. Force by charge, Newton by Coulomb, will give you the field, and that's why the formula becomes q by 4 pi epsilon naught r square. Is that okay, my dear warriors? Is that okay, my dear warriors? Okay, let's move on. Hold on. Yeah, okay. No, I don't want it this big. Sorry. Okay. An electric field line is a curved line in such a way that the tangent at each point on the curve gives the direction of the field at the point, which kind of makes sense because once again, yeah, please, yeah, because when you have a field line, the tangent is the one which gives me the correct direction. The tangent is the one on that curve which gives me the correct direction of the electric field at that point, and how close the field lines are. If the field lines are close, that decides the strength of the field. So if they are close, it's strong. If they are far away, it is a weak electric field. Correct? And in the regions of constant electric field, the field lines are almost parallel. They are parallel to each other. So there is no increase or decrease in the spacing between them. Keep this in mind. Yep. Yeah. Good afternoon, everyone. Almost evening now. Yes. Very good. Very good. Keep these things in mind. I hope you guys are remembering all these things. I hope you guys are recollecting these things as we revise through these important pointers, my dear warriors. Okay. Moving ahead over here. Some of the important properties of the field lines are continuous curves without any breaks. So if a field starts from a positive charge, remember, always starts from positive, ends at negative, it will not break. It is continuous. If it breaks, it is not an electric field line. Number two, the field lines cannot cross each other because then the tangents will be 2 in number. There will be no unique tangent. This can be a question. What are the unique or important properties of field lines? You will mention these 3 lines, you will get full 2 marks on this. Okay. Then the third important property is electrostatic. Field lines start from a positive charge and at a negative charge. That is something which I already told. In fact, you can also have a question on distinguish between electric field lines and magnetic field lines. So one thing you will say is electric field lines always start from a point and end at a point. Magnetic field lines are always closed loop. Correct? Electric field lines start from positive, end at negative. Magnetic field lines from a bar magnet appear to come from a north pole and end at a south pole, but even inside the magnet they continue their journey from the south pole to the north pole. That's how they complete their entire loop. That's how you can distinguish between them. You can get a question on that. Next, electric dipole is nothing but di means 2, pole means polarity. There are 2 polarities, positive and negative. So dipole is nothing but a combination of positive and negative charge. It's a pair like Pandu Champa, positive, negative. And there is a separation between them. And the net dipole moment, please, oh my god, I don't like this Adobe Acrobat here. It is random. I don't want this. Can I get rid of this? Please don't recognize anything. Oh my god. Alright. A dipole moment is a vector quantity. What is the direction of the vector quantity? It's from positive to negative? No. Field goes from positive to negative, but dipole goes from negative to positive. Bear that in mind. Okay, and the moment is the charge, either positive or negative, take any one of them, just the magnitude, multiplied by the separation between them. Keep that in mind. Okay, moving on. The field of an electrical dipole formula, you should remember this, P divided by 4 pi epsilon naught, but you should mainly remember it for a large distance. It is P divided by 4 pi epsilon naught r cube. P divided by 4 pi epsilon naught r cube on the axis. That means if this is the dipole, on the axis it is 2 times. On the equator, equator means perpendicular bisector, either here or here, it is nothing but 1 by 4 pi epsilon naught without that number 2. Why is there a minus sign? Why is there no minus sign? Simple. If the dipole is pointing here, on the equator the field points exactly opposite to the dipole moment. That's why the minus sign. On the axial point, that means on the axis, if the dipole is here, then the field is also that side only. That's why there is no minus sign. So when there is no minus sign, there is 2. When there is minus sign, there is no 2 over there, just the number P. Is that okay, my dear warriors? Clear? Yeah. This 1 by r cube is very important. It is not r square, it is r cube. Okay, keep this in mind, and this derivation I have done, and this is only valid for large r's, not for small r's. When you take a dipole and place it in somebody's field, it experiences torque, and that torque is P cross E. P is the dipole, E is the field, T is the torque. And then we go to the concept of electric flux, my dear warriors. What is flux? Flux is flow of something. Electric flux is flow of field lines. If I take a surface, how many field lines pierce through that surface is called as the or that is a measure of the electric flux. The flux is the field, how strong the field is into the area. So field into area gives me the flux. Okay, and you can see there is a dot product over here. So even if the field is at some direction, the area vector is always perpendicular to the surface. You take the dot product of the area vector and the field vector to get the flux, which is a scalar quantity. So there is a dot product over there. Okay, keep this in mind. Then you have the Gauss's law, my dear warriors. Yep, where do we go? Yeah, Gauss's law says that the total flux for a closed surface, my dear warriors, yep, is going to be nothing but dependent only on the charges which are there inside, not the outside charges. Okay, so it is Q by epsilon naught is the total flux. If you take a closed surface like cube, sphere, maybe even cylinder, cone, whatever, closed surface, the total flux will be Q divided by epsilon naught. If you take a long wire which is linearly charged, the field is given by lambda by 2 pi epsilon naught r. So imagine a long wire, the field due to that will be radially everywhere, like this, everywhere. So that is basically the field, and that is by lambda by 2 pi epsilon naught r. Okay, and all these are derived using Gauss's law. You should know the derivation. Second derivation you should know is of a sheet. If you take a large sheet which has charges everywhere, okay, so you take a large sheet, something like this. Where does it go? Where did it go? One second. If you take a large sheet like this and there are charges everywhere, the field lines are parallel to the sheet. The field lines are parallel here and here. So it is uniform, given by sigma by 2 epsilon naught. Very good. Sigma is the charge per unit length, per unit area. Sigma is charge per unit area. Lambda is charge per unit length. So lambda is generally used for per unit length, sigma is used per unit area, and rho is used per unit volume. Okay, per unit volume. You can see that over here for a shell. You should know the formula for it. If you are outside, it behaves like a point charge. Shell means hollow sphere. If you are outside the shell behaves like a point charge at the center. So that's why 1 by 4 pi epsilon naught Q by r square. But if you are inside the shell, no matter where you are, the net field is 0. All the field lines cancel out each other. Keep this in mind. Okay, moving on to the next one. Okay. Yeah. So all these are basically the symbol dimensions unit. Will you memorize this? No. In fact, I would say try to figure out the dimension using some or the other formula. If you can figure out the formula, dimensions or the units using some formula, that's it. That revision is done for all these quantities. Don't sit and by heart. Okay, let's go to some points of ponder. You might wonder why the protons all carrying positive charges are residing inside the nucleus. Why do they not fly away? You will learn that there is another force called as the strong force which holds them together, and that is basically, the nuclear force. Because many students ask, sir, why only electrons are participating in the current electricity? Why are the protons so lazy? Basically, these protons, neutrons, etc. in the nucleus, they are held by strong forces. They are called as the nuclear forces, and that's why they are not able to move. As the entire solid structure only will change, the wire, the conductor only will change its shape. Keep this in mind. Also, remember that the electrons are not allowed to sit on top of the protons, that is inside the nucleus, due to the laws of mechanics. Okay, they cannot just sit onto the proton, they will have to continuously be in some kind of orbit, some kind of state. You will learn that in atomic structure, or you have already seen that. Coulomb and gravitational force follow the same law of inverse square. Inverse square means you will see gravity formula or Coulomb's formula has r square below, isn't it? So basically that is called as inverse of the square law. But gravitational has only one sign, which is attractive, whereas Coulomb force can be of both signs, that is attractive or repulsive. That is very interesting distinguishing factor. Gravity is always attractive, whereas charges forces can be repulsive or attractive, because charges can be of two signs but mass is of only one sign. The constant of proportionality in the Coulomb's law is a matter of choice if the unit of the charge is to be defined in Coulomb's law. In SI units, however, what is defined is the unit of current, ampere, via its magnetic Ampere's law, and the unit of charge is simply defined as this. In that case, the value of K comes out to be this. Meaning, a lot of people think K value is 9 into 10 to the power 9 and it is constant no matter where. Guys, remember, they have some units, Newton, meter, Coulomb. So if you use CGS unit or British foot-pound system, this won't be 9 into 10 to the power 9. You will have to convert Newton into dyne, meter into centimeter, and so on and so forth. Coulomb into ESU. Then the value of K will be different. Please remember, K is not like pi value or E value. Pi is 3.142. It is not dependent on units or systems or anything else. So it is a proper constant, mathematical constant. K is not a mathematical constant. K is a constant and the value might change on the choice of the unit. That is what this point says. Now did you understand? Is it very helpful to all of you? Yep, very good. For questions, I have already conducted sessions. Please watch those sessions as well. Yes, definitely. Alright, moving on. The rather large value of K, that is the large size of the unit of charge, from the point of view of electric effect arises because the unit of charge is defined in terms of magnetic forces, which are generally much weaker. That's why while defining 1 ampere is a unit reasonable size, okay, 1 coulomb is 1 ampere second. So what they say is that 1 coulomb of charge is a very big unit for charge, because 1 coulomb means trillions and trillions of electrons or protons. Actual charge is 1.6 10 to the power minus 19. So why did we define such a big unit? Because charge is not a fundamental quantity, it's a derived quantity. I hope you remember that. Current is a fundamental quantity and charge is defined in terms of the current unit. So 1 coulomb is 1 ampere of current flowing for 1 second. That's how the coulomb unit comes, and that's why it ends up being so large. Otherwise, it had no other reason to be so large. Okay, this can be like give reason questions for 1 marker or 2 markers. The addition property of charges is not obvious. It is related to the fact that electric charge has no direction. It is a scalar. So when you add the charges, remember, many people think, sir, plus and minus, sir, won't it have direction? No, just because something has plus and minus does not mean it is a vector or it has a direction. Charge is a scalar quantity. Remember that, irrespective of the sign which it has. Okay, so don't think something has sign means it has direction, means it is a vector. No, this is a very good example of that. Charge is not only a scalar, under rotation it is also invariant of frame of reference. Example, kinetic energy scalar, but it is not invariant in frame of reference on relative motion, meaning that if you take a charge and move it, the charge won't change. But kinetic energy, you see, if you are moving with the body will be at rest. Kinetic energy will be 0. So kinetic energy depends on who is observing it. But charge is not like that. No matter who observes it, person on Jupiter, person traveling at speed of light, person stationary on Earth, all of them will see the same charge. So that is why it is independent of the frame of reference. The conservation of the total charge is a property independent of the scalar nature of the charge, and the conservation refers to invariance. Invariance means not changing, okay, in a given frame of reference. A quantity may be scalar but not conserved. Okay, on the other hand, one can have conserved vector quantity like angular momentum of an isolated system. Chumma, they have done some show off over here. It is not needed for CBSE level, even for JEE Mains level, but you know, they have given this. What it means is that just because something is scalar does not mean it is conserved, and just because something is conserved does not mean it is a scalar, and just because something is scalar does not mean it does not change with frame of reference, and just because something is dependent on frame of reference does not mean it is a scalar. Basically, they say scalar quantity, conserved quantity, and also frame dependence, they are all independent things. Each has their own things, correct? Each has their own rules, own, you know, sets of properties. So you cannot say just because it is a scalar, so it will be dependent on frame. Oh, that's why it will be conserved. No, you cannot say something like that. Okay, they are all independent. That is the meaning of this point. Otherwise, don't get confused. Sometimes the people who write this also know they want to show off their knowledge. I feel they can't write it in simple words. So chumma, they could have written down in simple words, but the way they have framed it, no, it feels like they want to be probably Shakespeare and who knows, God knows who, of the 21st century. Quantization of electric charge is a basic unexplained law of nature. Interestingly, there is no law in mass, meaning quantization, why does it come? Nobody knows, but it happens. Meaning the smallest charge. Why is the smallest charge 1.6 10 to the power minus 19? There is no explanation for that. There is no explanation for that. Okay, but you will also see there is no such rule in mass. Like there is nothing called as smallest mass. Mass can be anything. Okay. Superposition principle should not be regarded as obvious. Okay, because you know, people think, oh, it is obvious that this charge and this charge and this charge, they will not affect each other. They will all give a combined effect. It is not obvious, but it is an observed quantity. That is what the point number 9 actually says. Electric field due to discrete charge configuration is not defined at the locations of discrete charges. For continuous volume charge distribution, it is defined at any point in the distribution. For surface charge distribution, electric field is discontinuous across the surface. Okay, what is the meaning of discrete and what is the meaning of continuous? Discrete means the charge is here, 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 points are there. Continuous means everywhere smoothly. You can pace the charges everywhere. That is the meaning of continuous. And discrete means separate, separate, separate. Okay. So electric field due to discrete, meaning separate, separate charges, is not defined at the location of discrete charges. Makes sense. If there is a charge present here, what is the field at that point? Because the distance, r value will be 0. So if I use the formula kq by r square, r if I substitute as 0, it will become not defined. So you will not define the field at the place where you are placing the charge, which is kind of obvious. But for continuous systems, you can define it everywhere. Keep that in mind. Electric field due to a charge configuration with total charge 0 is not 0. Okay, but for distances large compared to the size of the configuration, the field falls off faster than 1 by r square, typically of the field due to a single charge. An electric dipole is the simplest example of this fact. Okay. Remember, just because the total charge on a body is 0 does not mean the field is 0, because the positive will be somewhere, negative will be somewhere. So the positive might give some field, negative might give some other field. They may not cancel each other. So even a neutral body can give an electric field. So don't be under the impression that neutral means no field. Best example is a dipole. Dipole is a neutral body, equal opposite charges. Still it creates electric field. Second point is, if you take a point charge, the field is proportional to 1 by r square. But understand, for big bodies, the field is not 1 by r square because of, multiple, things which are happening together, like superposition, vector addition, scale, all these things are happening together, and mathematically it turns out to be, falling much more rapidly. The field dies out much more rapidly than 1 by r square. Best example is of dipole. The formula for field for a dipole is 1 by r cube. R cube means it will fall faster. So that's what it says, that the field due to a big body will not be proportional to 1 by r square. It is not even 0. In fact, it will fall much more faster. And the best example is a dipole. Is this clear? Yes. Everyone with me on this? All right. let's move on then. Let's move on then to the next chapter. Where is it? Where is it? Where is it? Yes, LEPH 102. Where is 102? Yes, over here. Okay, next chapter. Electric force. I hope you are smashing the like button. If you have not yet done that, please do it. I'm seeing if you guys are chumma attending the class for the sake of it, but you know, you are not giving your Guru Dakshina. Let's see if you have given your Guru Dakshina yet or not. Have you given it? Very good. Very good. Awesome. Awesome. How many marks can we get if you only study summary and points to pointer? Abhinav, I would say most of the give reasons, most of the objectives, most of the standard questions, you will see they will be taken from the points to pointer and summary. Okay, so I won't be able to give you an exact number, but 100% some 20-30 marks you will be able to score just through this if you know it properly. Okay, electrostatic force is a conservative force. Work done by an external force equals and opposite to electrostatic force in bringing a charge from a point is this. Which is the difference between potential energy of a charge and the conservative force. What is the meaning of conservative force? A force which can conserve the energy. It does not cause any loss, like electric force, gravitational force, spring force, elastic force. They are conservative. Also, a unique property is when you move this body by this conservative force and back to the same point, the total work done by that force is 0. And if you move that body from one point to some other point, the work done is independent of the path. Okay, like you lift the mass like this and like this, work done by gravity is same as taking the mass like this and then like this. Same thing also applies for charges. No matter how you go, the work done is the same. And the work done is given by the charge into the voltage difference. The potential energy at a point is the work done per unit charge in bringing the charge from infinity to the point. That is the definition of that is the definition of potential energy. For potential, it is the work done per unit charge. For potential energy, it is just the total work done to bring the charge from infinity to that point. The moment you make it per unit charge, then it becomes the definition of electrical potential. Okay, and the formula is 1 by 4 pi epsilon naught Q by R square. Electrostatic potential at a point with position vector R due to a point dipole of dipole moment P placed at the origin is given by this one, the potential due to a dipole. Just like dipole produces field, it also produces potential, and the potential is given by 1 by 4 pi epsilon naught P dot R hat divided by R square. Is that clear? P dot R hat, you can also write it as P R hat cos theta or P cos theta divided by R square. R hat has a magnitude of 1. So you can also put a cos theta over there. When there are multiple charges, the net potential is due to all the charges. So what you need to do is just add the potentials. Potential is a scalar quantity. You don't have to worry about the direction. So add the potential due to 1, 2, 3, 4 and all of that, and you will get the total potential. Exactly. Yeah. Oh, lot of people from Salem. Very good. Nice to see all the Salem boys and girls out here. Vanakkam. An equipotential surface is a surface over which the potential is a constant value and the point charge concentric sphere centered at a location of the charge are equipotential surfaces. Field at the point is perpendicular at all these points, meaning that whenever you draw a field line, let's say this is the field line, equipotential surface is perpendicular to it. And what is the equipotential surface? You stand anywhere on the equipotential surface, the voltage will be the same. Equipotential, same potential, that's it. And where does the equipotential line travel from? Where does the field line travel from? It always travels from high potential to low potential. Always. If you are standing, you are tired. If you are sleeping, you are less tired. When you are standing, high potential. When you are sleeping, low potential. So you want to sleep, just like you might want to do today. And they say that, the highest tendency, the most desire for sleeping comes just before the examination, or the desire to think about something else comes just before the examination. Just after the exam, you don't feel like doing anything. You don't feel like going outside and playing sometimes. And suddenly you are wondering, why do I not feel like calling that friend? Why do I not feel like doing that time pass or playing the game or thinking about that college or thinking about someone? Suddenly it vanishes. It is all a gimmick. So the person who learns to control that can also excel in the examination. Sixth point, and you can, if you agree with me, let me know in the comments after the session or maybe in the chats in the live. Potential energy is stored in a system of charges, and it is a work done to assemble them. Just like your PT teacher or assembly teacher has to put in a lot of effort to assemble all the students and the morning prayer, same way the work done to assemble the charges is called as the potential energy, given by the formula 1 by 4 pi epsilon naught Q1 Q2 by R square. Correcto. Awesome. Next, when you take a dipole and place it in somebody's field, it also has some potential energy, and that is given by minus P dot E. So when there is a dot, you can use a cos also. So minus P cos theta. You should know the different positions of stable and unstable and maximum torque. Next, in electrostatics, field is 0 in the inside of the conductor. Just outside, the field is sigma by epsilon. So when you take a conductor, like let's say I'm a conductor, inside of me, inside my muscle, inside my skin, inside my bones, the field will be 0. And the reason is all the charges are only on the surface. That means only on my skin if I was a conductor, although I am technically. Outside, the field is perpendicular. So here the field will be here. 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 Always perpendicular to the surface. Always outside. Formula is sigma by epsilon. There is no 2 over here. When there is 2, when there is a sheet and the field is going here also and here also. So when there is going 2 ways, field is going 2 ways, then that 2 comes. When the field is going 1 way, then only 1 comes. Understood? And inside the conductor, because there is no field, there is no way potential can change. Remember, field only travels from high voltage to low voltage. So when there is no field, that means the potential variations are only not there. Because if one point was at high and one point was at low potential, immediately field will begin to flow. What is a capacitor? Capacitor is a system of 2 conductors which can hold charge, and they might be separated by an insulator like air or basically a dielectric medium. The capacitance is Q by V. Q is the charge held on any of the plates. V is the voltage difference between the plates or the conductors. The capacitance does not depend on the charge, it does not depend on the voltage, rather it depends on the geometry, shape, sizes and their positions. Like a parallel plate capacitor has a formula epsilon naught A by D. A cylindrical plate capacitor has a formula 2 pi epsilon naught L by log B by A. A spherical capacitor has a formula 4 pi epsilon naught 1 by A minus 1 by V. So it depends on the shape, size and all those things and the medium between them. If the medium between the plates is filled with a insulating substance like dielectric, then the field creates a net dipole moment in the dielectric medium, which causes polarization, because of which the capacitance increases. So when you add a dielectric medium of constant 3, capacitance will become 3 times more. If it is 5, it will become 5 times more. So capacitance new one is K times the old capacitance, where K is the dielectric constant, not to be confused with the Coulomb's constant. Keep this in mind. Yep. All right. Great. Why fear when Shreyas Sir is here, and why fear when the revision is going on? Concentrate on the class. Don't think about tomorrow. Don't think about the past. The biggest problem with most of the students is they are getting scared thinking what the paper might be tomorrow. If you think about the paper tomorrow, is it going to change the paper? Is it going to change the situation? No. So what is the best thing you can do? Even in the last minute, even in the last 5 minutes, if you can gain some knowledge, gain it. Who knows what might come, what might help you gain those marks. Next, when they are in series, the net capacitance formula is like parallel resistors. So this one. And when they are in parallel, add them like resistors in series. Exactly opposite. So that is what is given right over here. Okay. I hope you guys are able to see all of this. Give me a thumbs up, guys. Energy stored in a capacitor of capacitance C with charge Q is given by 3 formulas. All the 3 formulas you should know with the derivation. Half QV or half CV square of half Q square by C. All of them are equivalent. And something called as energy density. Remember, when you take a capacitor, one is positive, one is negatively charged. Field goes from positive to negative. The energy stored in that field. It's the electrical energy stored in the capacitor. That energy per unit volume, if you take per unit volume, small volumes, the energy density is half epsilon naught E square. Thank you, Krishna, for Warrior Pandu's whistle puduing. Yep, yes. Great. Thank you, Priya Arul. Derivation deleted for energy. Okay, fine, good. Thank God. So, what should you do over here? Put it up in the chat box for all the new students out here. Will you memorize these dimensions? Will you memorize these units? How they are coming? No, you can get them very easily. Very easily if you remember the formula, like capacitance is Q by V. Capacitance is Q by V. So charge is coulombs and voltage is volts. So volts you can write it in terms of joules per coulomb, and coulomb is ampere second. From that you can get it. That's how you do all these things. Cool? Okay. Regarding the points to ponder, electrostatics deals with forces with between charges at rest, but there is a force on the charge. How can it be at rest? Thus, when we are talking about electrostatic force between charges, it should be understood that each charge is being kept at rest by some unspecified force. That is obvious. Okay. I mean, a lot of people think, sir, K Q1 Q2 by R square, that is electrostatic, static, stationary. How is it stationary, sir? Obviously, there is somebody holding it to, and then you are measuring the force. That is like obvious. Okay. A capacitor is so configured that it confines the field lines within the region of the space. So even if the field may have a lot of strength, the voltage between the two conductors of the capacitor is going to be very, very small. So understand this. When you take two parallel plates or two cylindrical plates, one is positive, negative, the field lines only flow between those plates in that small region. All the field lines are within that small confined region. So even if the field might be very strong, because the distance is very small, that's why the voltage between them is small. Because voltage is field into distance. Voltage difference is field into the distance that you travel. Distance is small, so voltage is also small. Field is discontinuous on the surface of a spherical shell. It is 0 inside and sigma by epsilon naught outside. Electric potential is, however, continuous across the surface, and it is equal to Q by 4 pi epsilon naught. This comes from the graph also. If you remember the graph, I had shown this to you, all of you, if you remember this. Yes. So if you talk about the electric field and electric potential, how do the graphs look like? So for the field, it is basically 0 inside and suddenly it goes like this. So there is a discontinuity here. For potential, it is constant inside and then it goes like this. So it is continuous here. That is what this is saying. That's all. If you know that, that is more than enough. Torque causes it to oscillate about E only if there is a dissipative mechanism. The oscillations are damped and a dipole eventually aligns with E. So what it means is, imagine the dipole is here and the field is somewhere here. The white one is the dipole and the field is the black one. So because of that, there will be a torque. So the dipole will experience a torque, will come here, but because of the momentum, it will go here. Then again, it will experience a torque here, it will go here. So it will end up oscillating because of the torque and it will perform simple harmonic motions. But if there is a resistive force, damping means something which takes away the energy, then what will happen? It will oscillate like this, and finally it will settle down in the direction of the field. But if there is no damping, it will continuously keep on oscillating. That is what it says. The potential due to a charge at its own location is not defined. It is infinite. Makes sense. I told you this before also. If there are multiple charges, you go at the charge. If I ask you the field, answer is not defined. If I ask you the potential, that is also not defined. So please remember, potential on the charge, because R will become 0. It is not defined. In that, in the expression QVR for potential energy of charge, VR is the potential due to the things, charges, external charges, and not a potential due to Q. As seen in point 5, the expression will be ill-defined if it includes the potential on the charge itself. It kind of makes sense. So, my dear students, if for example, there is a charge somewhere over here, and if I ask you what is the energy, then you might take the potential energy due to this charge, due to this charge, due to this charge. So you will take potentials due to each one of them. You will find the total potential, and when you multiply potential with charge, that's when you will get the total energy. Potential due to all the charges into the charge gives you energy. This potential is due to other charges, not the potential due to this charge. How can you find the potential due to this charge at this point? It is not even defined. That is what it is saying. Cool? Very good. Awesome. Very nice. Awesome. Let's keep moving. Very good. Keep it going. Yep. Great. Next, a cavity inside a conductor is shielded from outside electrical influences. It is worth noting electrostatic shielding does not work the other way around. That is, if you put charges inside the cavity, the exterior of the conductor is not shielded from the fields inside the charges. What it means is that, say for example, you take a conductor. Here also you take a conductor. Let's say you put a charge here inside, and here you put a charge outside. Why is it not coming? Okay, when you put the charge outside, what happens is the field lines go here, and they stop. After that they stop because the field gets obstructed by the conductor, and inside the conductor the field is always 0. So the field inside is 0. So in a way you are basically shielding yourself from the outside field. But when the charge is inside, then the field lines not only reach here, but they also end up inducing some charges over here, and these induced charges, they create a field outside. And because of this, you can sense that, oh, there is a charge inside. But if you're inside the conductor, you will never know whether there was a field or a charge outside of the conductor. That is the difference. Is that clear? Everybody with me? Understood? So when you are inside, you will never know if there was a charge outside. But if you are outside, you will know if there was a charge inside, because the field lines will create induced charges, and always outside a shell or outside a conductor there is field. It's only the inside of the conductor where you never experience any kind of field. Very good. Cool. So let's close this. Alrighty. Now next one, LPH103. Open with, add up. Great. Cool. Current, electricity, everybody ready for it? Current through a given area of a conductor is the net charge passing per unit time through the area. Current through a given area of a conductor, current through a given area of a conductor is the net charge passing through that thing per unit time through that area. Makes sense? Current is charge per unit time. So how much charge, coulombs goes per second, is the current passing through it. If you want to maintain a steady current, we must have a closed circuit in which an external agency moves the electrical charge from lower to higher potential energy. The work done per unit charge to take it from low to high is called EMF of the source. Note that EMF is not a force, it's the voltage between the two terminals. See, imagine you are cycling, or you are walking, or you are running a marathon. You go up a road, up a hill, down a slope, up a hill, climb a bridge, climb down the stairs, something like that, and you come back to the same point, you complete a lap. So understand, when you come back, you might probably drink some juice, you might drink some energy pack, some energy booster, some Glucon-D or something. So same way for charges also, it's like that only. So the charges might go through a bulb, through a fan, through a resistor, through a capacitor, whatever, and they come back to the same point. So once the current has come back, it needs that boost up, that energy that comes from the battery, which is EMF, E. So EMF is the work done to move that charges from lower potential to higher potential. Why? Because once they are back, they are on low potential, negative terminal, and now they have to be sent to positive terminal, which is at a higher voltage. So to do that, you need to boost them up, pump them up. So that is called as the EMF. It's the work done per unit charge that you need to take it from the lower to the higher potential. The definition of EMF comes from here. If they ask you, write it, draw the diagram, also show the symbol of EMF, etc. And mention that EMF is not a force, it is the voltage difference between the two terminals of a open circuit voltage, because when it is closed, the voltage is E minus IR. So when there is current, the voltage across it is less than EMF. When it is not flowing any current, then only the voltage is equal to E. Otherwise, it is V is equal to E minus IR. How many of you remember this? Great, very good. Ohm's law says that the current flowing through a substance is proportional to the voltage. Such a device is called ohmic devices. It gives you the definition of resistance. V is equal to IR. 1 ohm is 1 volt per 1 ampere. Resistance of a conductor depends on two things, length and the area. And yes, one more thing it depends on is the material. So rho is the material's property, L is the length, A is the area of cross section. Rho is also called resistivity. It also depends on the temperature and other things. So if you heat it up, the resistivity might go up. If you cool it down, the resistivity will also go down. For non-conductors, rho is very high. For conductors, rho is very low. Resistivity varies over a wide range. Metals have very low resistivity, and semiconductors are somewhere in between, the same point which I just told you over here. Now, in most of the objects, the carriers of current are electrons. In some cases, like ionic crystals and electrolytic liquids, positive and negative both carry current. I think I told you this before. In pure conductors, only electrons are participating in current, but in electrolytes, some ionic crystals, right, both the positiveness and the negative ions, they both participate in the conduction of electricity. Current density is N, V, D and E. E is the charge, which is Q over here. N is charge carriers per unit volume. VD is drift speed. J is the density, which is current per unit area. Remember, for electrons, the charge is negative E. Remember that. J is the current density vector. It is always in the direction of the current. Okay. Then using electric field is voltage per unit length only, you get this formula of I is equal to NVDR. And using Ohm's law and other things, you will get this relationship, which is E by M. Charge into field by the mass of the electron is resistivity into number of electrons per unit volume into E square is charge square by mass into VD. Okay. You should know the drift velocity formula also, which is EE tau by m. Tau is called as the relaxation time. E is the charge, E is the electric field, m is the mass. So arranging those equations, you get the resistivity also. Resistivity is mass by me square tau. Tau is the relaxation time, meaning from one collision to the next collision, how much time does it get to relax? N is number of charges per unit volume which are available in the conductor. M is mass, E is the charge. The temperature range in which resistivity increases linearly, you define the coefficient of resistivity alpha, alright, which is the linear coefficient of thermal resistance. Remember, when you increase temperature, resistance also increases, but it is not linearly proportional. Sometimes it increases more rapidly, then it is less rapid. So there is a small range where it is linearly proportional. Only there you can use the formula, which is R is equal to R naught 1 plus alpha delta T. Otherwise, you cannot use it. When you connect, Ohm's law is obeyed in many objects, many substances, but it is not fundamental. Like V depends on current non-linearly, then it fails, okay? Or the relation between voltage and current depends on the sign of the voltage for some value, or the relation between V and I is non-unique. Meaning there are some objects where voltage and current are non-linear. Sometimes how the voltage is fluctuating defines the current. Whether voltage is increasing, current will be this. If voltage is decreasing, current will be that. So in those devices, you cannot use V proportional to I. Those devices are called non-ohmic devices. Okay. And one such example is GaAs, gallium and arsenic. So this was also an example. In GaAs, will V be proportional to I? Answer is no. Okay. When you connect a battery to an external resistance, then the external voltage across the resistor is given by IR, current into resistance, that's Ohm's law, and current will be the total EMF, look at it, the total EMF by the total resistance. Total EMF is E, total resistance is R plus small r. What is small r? Internal resistance, correct. Kirchhoff's two rules you should know, junction rule and loop rule. Junction rule and loop rule. What is junction rule? Junction rule means current entering in is current going out. Kirchhoff's loop rule is nothing but the total sum of the voltages across a circuit is 0. Junction rule is based on conservation of charge. Loop rule is based on conservation of energy. Wheatstone's bridge is where you have 4 resistors arranged in a peculiar way, and the bridge is said to be balanced if the ratio of the resistances are equal, and then any device that you connect in between the bridge will not have any voltage drop or no current also flowing through it. So you can completely neglect such a device connected in that bridge, right? So these things, though, you have to know the formulas, only then you can know the dimensions. You cannot sit and by heart these dimensions. If you know the formula, this remark is very important. From the remark, you can get this. From the remark, you can get the units also. Got it? Cool? Points to pointer. Current is a scalar, although it is represented with an arrow. Currents do not obey the law of vector addition. This is a very famous give reason question. Why is current a scalar quantity? How many of you have seen this even in JEE NEET exam? Sangeeta, this is a revision session. Yep. Great. Yeah. So this is a very famous question. Current has a direction, arrow mark, but it does not follow the rules of vector addition. So that's why it's not a vector. In fact, current is the dot product of density into area. J dot area is the current value. Dot means scalar. Refer to the current voltage curves of a resistor and a diode, and you will see that resistor has a linear graph, whereas the current versus voltage graph for diode is non-linear. So meaning that the voltage and the current are non-proportional to each other. So that is a non-ohmic device. Okay. But you can still use V is equal to IR. That is the point. Although V is not proportional to I, still how are you able to use V is IR? Meaning R is going to change. So even for a non-linear curve, when you use V is IR, R gives you the resistance at that voltage or at that current. It means also resistance is continuously changing, which is not the case with pure conductors. In conductors, no matter what your voltage is, the resistance remains the same. But for semiconductors, the moment the voltage changes, resistance also changes. That's why it is not going to obey Ohm's law, directly proportional law. It will be non-linear device. Homogeneous conductors like silver or semiconductors like pure germanium or germanium containing impurities obey Ohm's law within some small range, but if the field becomes strong, they are going to be departing. Just like you have the thermal resistance coefficient defined for a small range of temperatures where it is a straight line graph. On a big curve, a small part of it is straight. Even on a big curve, a small part might be straight. There you can define linearities. So same way, even for semiconductors, you will see when the graph is curved, for a small range, the graph might be linear. There you can use or say that voltage is proportional to current. That's what it says. The motion of the conduction electrons in a field is the sum of the motion due to collisions and that due to the field. The motion due to random averages to 0 and does not contribute to drift speed. Thus is only the electric field is only due to the electric field applied on it. Meaning, whenever you see a conductor, there will be one electron going like this, one electron going like this, one electron going like that. Everywhere they are going randomly like mad fellows. The average of them will be 0. One going here, one going there, cancel out, gone. But when you apply electric field, not only are they randomly moving, but at the same time they are also slowly drifting like this. Like you see, these electrons which were on one side of your screen are slowly moving randomly and at the same time also slowly going out from the other side of the screen. So that is what electric field does. It slowly drifts the electrons. The random motion is because of thermal energy collisions. The relationship density is rho into V should be applied to each type of charge carriers. So the total current density is because of positive and negative. Now what happens is for an electrical conductor, the positive charges don't move. This V is basically your mobility, nothing else. Okay, but for things where both positive and negative charges move, you should consider both the current densities. What it means is that, see, for a conductor only the electrons move. So when you measure current density or conductivity, all these things, you are considering only the current density due to electrons. What about current density due to the nucleus or the positive charges? You don't. Why? Because I know the nucleus is at rest. But if you take an electrolyte, but if you take a semiconductor, their holes are there, positive, and electrons are there, negative. Both of them are moving. Both of them participate. Both of them participate in electricity. So you should consider the total current density due to positive as well as negative charges. That's what it says. Kirchhoff's junction rule, KCL, is on conservation of charge. I just told you. Okay. So please don't think that, sir, I thought one current was coming here, one current was coming here. So both these currents cancelled out when the currents were joined and you formed a T-shaped junction. No. The direction of the current like this or like this does not matter. If it is coming in or out, that's all that matters. Whether it came at 60 degree, 40 degree, 90 degree does not matter. In and out matters. That is what point number 6 tells you. Okay, is that clear? I believe many schools, many people do not discuss this points to pointer, and it so happens that you end up getting these points to pointer or summary points in the exam, and then you are like, sir, where was this in NCERT? I searched. Then you realize, oh sir, it was in summary. Oh my god, I didn't read the points to pointer. So you're going to lose a lot of marks. If you are aiming for high percentage or even basic percentage in physics board examination or even in NEET JEE, you should look at these things. Moving on to the 4th chapter with me. Are you showing your full energy and josh and support towards the channel? If not, it is going to come and bite you. You have to show your full love and support, full dedication. Only then the knowledge will be imparted properly. Okay, let's go. Does VD averages to 0 due to random motion? See, VD is the average velocity of the electrons due to the electric field. So the thermal energy does not affect the thermal energy, or the thermal collisions does not affect drift speed, if you think about it, because you know the actual individual velocities of the electrons, they will anyways average out to be 0, but there will be some velocity left after that because of the battery connected, which gives you the electric field. But if you turn off the battery, the electric field goes away, then the drift speed becomes 0, because then the actual velocities will completely cancel out. There is no bias towards one side that okay, some velocities are more, some velocities are less. There is nothing like that. They will actually end up cancelling. But when you turn on the battery, the field produced increases the speed on one side, decreases the speed on the other side, thus creating that notion or the sensation of drift. I hope that is clear. All right, let's move to the next one. Water break, quick water break. We have reached magnetism. We have to complete all the chapters. We have to complete all the chapters. Next, the total force on a charge moving with speed v in the presence of magnetic field and electric field is given by Q V cross B plus electric field. V is velocity, B is magnetic field, E is electric field, Q is the charge. And remember, this is called as the Lorentz force. The first part, be careful, velocity cross magnetic field, you have to look at the directions using right hand thumb rule. The second part is just charge into field. So that means the force will be in or against the direction of the field. When you take a wire which carries some length with some current, the force on it is I current, L length cross B. Again, there is a cross product. When you take a magnetic field, the charge which executes circular motion in a plane perpendicular to B, the frequency is of the cyclotron frequency given by this. This frequency is independent of the particle speed and the radius, and this is what is exploited in the machine, which is used to accelerate the charged particles. So I believe cyclotron is removed if I'm not wrong, but still you should just know the frequency of any charged particle going in a circular orbit. So when you throw a charge perpendicular to the magnetic field, then the charge goes in circular motion, and the radius of such a orbit is mv by qb. The time period of such a circular path is 2 pi m by qb. 1 by time period gives you the frequency. The time period or the frequency does not have the radius or the velocity inside that formula. Bear that in mind. When you use Biot-Savart's law, the magnetic field due to a small wire element which is carrying some current is given by mu naught by 4 pi. Mu naught is permeability. Mu naught by 4 pi is 10 to the power minus 7. I is current. dl is the length which is causing that field. Cross r. What is r? R is the position of the point where you are measuring the field. Divided by r cube. R cube. Keep this in mind. Yes. Very good. Now to obtain the total field, what will you do? You will find the field due to one element, another element, another element, another element. So you will add the fields. That means you will integrate. That's why you must integrate the vector expression. When you talk about the magnitude of the magnetic field due to a loop of r radius carrying some current at a distance x, the formula is mu naught I r square, r is the radius, by 2 x square plus r square raised to 3 by 2. What is x? Is the distance from the center of the axis. When you are at the center, the value of x will become 0. If you put x as 0, you will get this. It will be mu naught I by 2r. That's all. Just like you had Gauss law in electrostatics, you have Ampere's law. You have Ampere's law in magnetism. So the total magnetic field dot, not the area vector, it is the length. You find the magnetic field, take the dot product with length. Go ahead, find the magnetic field, take the dot product with length. You keep doing that and come back to the same point. That's why the cyclic integral will be mu naught into current. Mu naught is permeability, I is the current which is inside that path. So if I went from here and came back to the same point, if I went and came back from one point to the same point, all the current wires which are passing inside that loop are considered here. If there was a current wire passing from outside, do not count that over here. Current enclosed by the loop. The magnetic field at a distance r of a long wire carrying some current using Ampere's loop law comes out. So this derivation very important. Mu naught I by 2 pi r. It's using purely Ampere's loop law. The magnitude of the magnetic field in a long solenoid. Again the second derivation using your Ampere's loop law for a solenoid. What is a solenoid? It's an electromagnet. You take a tube and wind a coil. N is the number of turns per unit length. You will get the field as mu naught small n I. What is small n? Small n is the how many turns are there per length of the solenoid. When you talk about parallel currents, then or anti-parallel currents, then one wire will cause a magnetic field. That magnetic field affects the current on the other wire, and that applies a ILB force. So one wire produces magnetic field, other wire gets affected by the Lorentz force. So if the wires are in the same direction, you will see that they will attract. But if they are in opposite directions, then you will see that they will repel. So same directions they will attract, opposite directions they will repel, and the formula also you should know mu naught I1 I2 by 2 pi d, that is the force per unit length on those wires. When you take a wire and bend it into a coil, that coil carrying current behaves like a small electromagnet. The small electromagnet will have a north pole and a south pole, means it's a dipole now. So it also has a dipole moment given by, just like NTA, you have NIA, National Investigation Agency. But N over here is the turns of the loop, I is the current, A is the area. Just like a electromagnet will have dipoles, so a coil carrying current will also behave like a small magnetic dipole. So the dipole moment is given by NIA. Just like in electricity you had torque on a dipole, right? Same way over here you have torque on the magnetic dipole. Instead of P cross E, it is magnetic moment cross magnetic field. You will also have energy, which is minus m dot b. Obviously force on a dipole is always 0. Whatever force acts on the positive will act on the negative. They will end up cancelling out each other completely. Moving coil galvanometer sensitivity formula I have already told you before as well, that it is the deflection per unit current and all of that. It is NBA by K. Phi by I, you take I below, you will see it is NBA divided by K. NBA is basketball. Basketball you play with hand, you never kick it. Kick, K is below. So NBA by kick, K is below in the denominator. That's how you remember this formula. Moving coil galvanometer is a device used to measure current. When that is passed, the current in that coil is going to produce a magnetic moment. That magnetic moment will experience a torque because of the strong magnets which are around it. So it will deflect, and there is a spring to stop the deflection after a point, and then you measure the deflection, and that's how you measure the current. You will see that the deflection is directly proportional to the current passing through it. You can convert it into an ammeter by connecting a parallel resistance called as the shunt. So you bypass the current into the shunt, thereby protecting the galvanometer, because galvanometer cannot take in large current. So you bypass it by a shunt when you want to use as an ammeter. So when you use a parallel resistance, the total resistance becomes small. That's why ammeter's resistance is negligible, and that's why you also use ammeter in the circuit as it is in the same branch. You do not use it in parallel. Whereas when you want to convert it into voltmeter, you connect a series resistance with the galvanometer, and that is very huge resistance, thereby increasing the resistance of the voltmeter. So you never put the voltmeter in the same branch, you connect it parallel and you measure the voltage across that device by connecting it in parallel. Great. So all these things are there. Let's go to points to pointer. Everybody with me? This is for both. This is for both. Frank, I would say don't worry about when the session started, when the session gets over. just go with the flow. Right now you need somebody in front of you who is just teaching rather than you wasting your time thinking what to do, what not to do. If you are a student who does not know what to do, attend this class. If you are a student who is not confident, attend this class. If you are a student who wants to just pass, just attend this class. If you are a student who wants to make sure you don't even lose 1 mark, you don't want to lose 1 line also, attend this class. Remember this, okay? Whatever you had to do, you have done for the last 1 year or 2 years. Okay? You might still not be confident. That's the reason why you are here. So make the full use of this particular class. You will see the complete benefit tomorrow. Electric field lines always start from positive to negative, but magnetic field lines are always closed loops. That was one difference which I already mentioned. There is no start, there is no end. This discussion in the chapter holds for currents which are standard, steady, does not change with time. When the currents vary with time, Newton's third law is valid only if momentum carried by the electromagnetic field is taken into account. So basically here, when the wire is carrying current, the current is constant. You do not take into effect that current is increasing, decreasing. But if current is increasing, decreasing, then the magnetic field will increase, decrease, because of which what will happen, there will create a electromagnetic wave, which is an EM wave. So that will create a generation of an electromagnetic wave. Electromagnetic wave means photons. Photons means it has momentum, and momentum effects has to be considered. Basically, they are saying that don't worry, only constant currents are considered. All those random effects are neglected. That is the simple meaning of it. When you use the expression of Lorentz force, QV cross B plus E, velocity dependent force has occupied the attention for some greatest scientific thinkers. This is not so important, okay? So don't worry about this particular statement in points of pointer, because it talks about how you change the frame of reference and how the electric field and magnetic field might also change with the frame. So ignore this pointer. It is not even important from JE point of view. Ampere's circular law is not independent of the Biot-Savart's law. This can be derived from this. The relationship is similar to Gauss and Coulomb's law. See, Coulomb's law cannot be derived, but if you assume Coulomb's law, you can derive Gauss law. Same way, Gauss law can't be derived, but if you assume Gauss law, you can derive Coulomb's law. Same way, if you assume Biot-Savart's law, you can derive Ampere's law, and if you assume Ampere's law, then you can derive Biot-Savart's law. So Biot-Savart's law and Ampere's law are not independent, they are dependent. If you know this, you can derive this. If you know this, you can derive that. Okay, got it? So you have to assume either this or that. The other one automatically is derived from the other one. Got it, my dear warriors? That's the fourth point. Great. Let's move on to the next. Guys, come on, show your full josh and full energy. I believe very few teachers or nil lectures would be done on just the summary and the points to pointer for your competitive exams or board examinations on YouTube or even otherwise. So make the full use of this, because this is going to be a game changer for your tomorrow's examination. Thank you, Krishna. All right, let's begin. How to guess passing marks? Well, to watch this class at least, you'll get passing marks. And watch my older classes, you will get some questions from that, 100%. And the graph sessions, the derivation sessions, you watch it, forget passing, you will do very well in the board examination. The science of magnetism is old. Okay, we have gone to the next chapter, my dear warriors. This is the 5th chapter, magnetism, properties and all of that. Magnetic materials tend to point in the north-south direction. The magnetic poles repel, unlike ones attract, and cutting a magnet leads to smaller magnet. Magnetic poles cannot be isolated. This is like pretty much standard. Magnetism was known since a long time. Many scientists knew that some things mysteriously attract and repel each other. Just like positive and negative charges, you also have two polarities. Same polarities will repel, opposite polarities will attract. Even if you find a stone which is magnetic in nature, if you break it into two parts, don't expect you will get two poles apart. No matter how much you break it, you will always get two smaller magnets. Keep that in mind. You can never isolate the two polarities. It is always bipolar dipoles. You take a bar magnet, it is placed in a uniform magnetic field. The net force on it is 0. When a bar magnet is placed in a uniform magnetic field, the force on it is 0. Yes, in fact, any dipole, be it a coil carrying current in a magnetic field, be it an electric dipole in a magnetic field, always, or a bar magnet in a magnetic field, Earth's magnetic field, doesn't matter. The net force is always 0. Torque is m cross b. Potential energy is minus m dot b. Simple. A bar magnet can be also assumed like an electromagnet or a coil carrying current. The derivation you should see. In fact, you will see that the formula for the magnetic field on the axis and on the equator. If you take a bar magnet on the axis and on the equator, the formulas are also similar. Look at it, just like electric dipole. For the axis, it is mu naught m by 2 pi r cube. So actually, if you put 4 pi over here, there is that number 2 over here. Whereas on the equator, it is mu naught by 4 pi m by r cube. Instead of electric dipole, you have the magnetic dipole. Instead of 1 by 4 pi epsilon, you have mu naught by 4 pi. So everything is similar. In magnetism, Gauss's law can be applied, but the right hand side of the Gauss law, which is the total flux, will always be 0, because magnetic field lines are always not circular, closed loops. Whatever comes in goes out, whatever goes out has to come in. Flux in is flux out, so total flux in a closed surface is 0, because nothing will originate, nothing will terminate. This is Gauss law in magnetism. Total magnetic flux is always 0. Okay, this is the magnetic intensity, which is H, which is B naught by mu naught. Standard formulas. The magnetic field is mu naught into H plus M. M is called magnetization of the material. Okay, and the magnetic field B is the magnetic field inside the material. H is the magnetic intensity. How to remember the difference between H and your magnetization? M for magnetization. M for magnetization. Sometimes people also use the symbol I and also call it intensity of magnetization. It basically tells you how much is the material magnetized, how much is the intensity with which the material got magnetized. So you use the symbol I generally instead of M in many books. So intensity of magnetization is the magnetic dipole moment per unit volume. So if I magnetize iron, how much did it get magnetized? What is the intensity of it? That is the intensity of magnetization, and you can use the symbol I or M. Magnetic intensity is the measure of how intense the magnetic field was from outside to magnetize it. Maybe I took that iron and I placed it in somebody else's field. So that is H. H is external. H is external. M or I is the internal, the material's effect. How much did it get affected? For linear material, magnetization or intensity of magnetization is susceptibility into H. B is mu H, standard formulas. Relative permeability is 1 plus susceptibility. This is the relative permeability. Remember, it is permeability upon permeability of vacuum. Magnetic materials are classified as dia, para, ferro. Diamagnetic susceptibility is negative. For para, it is small positive. For ferro, it is highly positive. Objects which are at room temperature retain their ferromagnetic property for a long time. They are permanent magnets. Ferro means they are used for making bar magnets, permanent magnets. If you heat them beyond a certain temperature called as the Curie temperature, those magnetic properties go away and they became temporary magnets. Then from ferro it goes to paramagnetic. That switch happens at a temperature called as the Curie's temperature. You should know this. All these are the symbols and the formulas and their units and their dimensions. A satisfactory understanding of the magnetic phenomena, all these pointers over here, this is history. Don't have to go in history, don't worry about it. Okay, magnetic monopoles do not exist if you slice a magnet into half. Okay, so what is the second point? If you take a body, you start breaking it into small parts, then it becomes a cell, maybe then it becomes an atom, then that atom has protons and electrons. You get electron and protons, which are the smallest charges. But the same thing you cannot say about magnets. No matter how much you break them, you will never get north pole and south pole separately. That's why magnetic monopoles do not exist. There is no thing called as elementary pole, elementary magnet, or you cannot say magnetism is quantized like in electricity. Okay, keep that in mind. Another consequence of the fact that monopoles do not exist is that field lines are continuous and closed loops, whereas electric field lines start and end. Makes sense, because electric field starts from positive and goes till negative. That means there is something called positive, something called negative. But field lines of magnetism never start and end. They are closed loops. So there is nothing like north which you can precisely pinpoint over here, or south which you can pinpoint over there. Got it, my dear warriors? Very good. Okay, very good, very good. Awesome. There exists a perfect diamagnet, namely a superconductor. This is a metal at a very low temperature. Okay, in that case, susceptibility is -1. Perfect diamagnet, meaning diamagnets repel other magnetic field. Susceptibility is -1. That's a very good diamagnet. The relative permeability is 0. That means whatever field comes from outside, it will perfectly cancel it out. No field will be there remaining inside. Permeability is 0. Relative permeability is also 0. That is going to be a superconductor. This is also a perfect conductor. Okay, so perfect conductor also is a perfect diamagnet, and this was proposed in 1957 and it was recognized for Nobel Prize in 1970. So this explanation, this theory, alright, it won Nobel Prize, a very important thing. Diamagnetic is universal. It is there in all the things. Even I am diamagnetic, even you are diamagnetic. I'm not saying diabetic, I'm saying diamagnetic. Okay, don't say diabetic, diamagnetic. Everything is diamagnetic. But when paramagnetic and ferromagnetic property is more or is dominant, then you say that the material is para or ferromagnetic. Understand, a paramagnetic and ferromagnetic material is also diamagnetic. Okay, but a diamagnetic material is only diamagnetic. It has no para and ferro. Many people do not know this. We have classified the materials as dia, para, ferro. However, there additionally exists materials such as ferrimagnetic, antiferromagnetic, spin glass, etc. Why did they write this one? To show off. Is this going to be asked? No. But you should know that, okay, there are other materials also. So, chumma, for show off, okay? Like there will be always one student in the class, ma'am, in black holes, no, you know about Stephen Hawking's radiation, ma'am. Teacher is teaching units and dimensions. Student is telling black hole, Stephen Hawking's radiation. Next level student. So this pointer is exactly like that. Okay, cool. Let's go ahead. Sixth chapter. Wow, we are completing so many things one by one. All right, clearo. So yes, so finally we are on to the next chapter, and let me tell you, I am also extremely tired because I have driven for almost 890 kilometers or something, yeah, from Pune to Bangalore, right? So I was the driver, I was driving, and I didn't sleep. And now I'm here to take your class, and all of this so that I could take it from the studio. That's it. You guys were eating my head. Sir, please take from studio, please take from studio. So I am back over here. Anyways, so I hope this video reaches as many students as possible and you all get benefited from it. Right, the magnetic flux through a surface placed, flux. Just like electric flux is E dot A, magnetic flux is B dot A. Flux is a measure of the field lines passing through it. So just like E dot A, you have B dot A. Magnetic flux is in Weber. Weber is only for magnetic flux, not for electric flux. Now when that flux changes, so magnetic field is more, it became less. Magnetic field is less, became more. Maybe area increased, maybe the angle changed because there is a dot product. So theta changes, flux changes. Then the flux change causes electricity to be induced. That electricity EMF induced is directly proportional to the rate at which the flux changes. That is Faraday's law. Why the minus sign? That is because of Lenz's law. It says that the electricity induced is always going to oppose the change. So if the flux tries to increase, the current which is produced inside the coil will try to oppose that increase. But if the flux is decreasing, then the current produced in it will try to help that flux and it will try to increase it. It will try to strengthen it. So it always opposes the change. It always opposes the change. Yep. So, sir, if you study full NCERT, will you get full marks in JEE? No. You have to solve problems. Yes, Gryffindor team, I came in car. Now, don't ask me why. Okay. Let's move on to the next one. When you take a rod and move it, and you move it in a magnetic field, the rod develops polarities. It behaves like a battery, and that is why, because it is moving, that's why motional, and because it behaves like a battery, hence EMF. Motional battery means EMF. So moving rod produces EMF given by BLV. The rod's motion should be perpendicular to the magnetic field and the length also should be perpendicular. Otherwise, if the length is in the direction of the field, velocity also in the direction of the field, then there is no EMF which is produced. Inductance is flux divided by current. In fact, flux is equal to L into I. Inductance is a property which tells you how much it is going to dislike any changes of the current. The moment current changes, it will be like, hey, decrease or increase. It does not like any changes. It wants it to be steady. That is inductance. And how does it do that? By producing EMF. So if the current is reducing, it gives in EMF to help the current. It tries to increase it. If the current tries to increase, then the EMF will try to decrease that current. So that EMF is inductance into rate of change of the current. L into di by dt, M into di by dt. Now when do you use L? When do you use M? If the EMF produced is in the same coil and the current which is changing is also in the same coil, so that is self-inductance. But if the current is changing in one coil, the EMF is produced in another coil, then that is called mutual inductance. So formulas are very similar, only the symbol will change depending on the scenario, whether it is on itself or on each other. Then you use mutual. You should know the self-inductance formula for a solenoid, which is mu naught n square Al. That's the formula. Yes, that's the formula. Very good. Mu naught n square. N is number of turns per unit length. A is the area of cross section. L is the length. In a generator, what you do? You take a coil, rotate it in a magnetic field. So because the angle changes, flux changes, Faraday's law. Electricity is created. And that electricity created is sometimes positive, negative, meaning sometimes this way, sometimes the other way. That is alternating current. So alternating current is produced by rotating a coil inside a magnetic field. The formula is BA omega. If you see, this is omega, 2 pi f. 2 pi f is omega. BA omega n sine omega t. That was the formula. Okay, I have been telling you this again and again. I am repeating it for you. All right. Now, always in points to pointer, generally the first point is more like history or something which is not So important, but yeah, the same thing is over here. Ampere and others established moving charges produce magnetic field. So you can see it's more of history than of any use for us in board examination. In a closed circuit, electric currents are induced to oppose the changing flux. It is as per the conservation of energy. However, in case of open circuit, EMF is induced across its end. How is it related to flux change? So basically what they say is, if you have a coil, then the current is induced to oppose the change in the flux. Makes sense, because that current will flow in the coil. Any change that is happening, it will be opposed. It is as per law of conservation of energy. But when you have an open circuit, meaning it is not a coil, then how do you say that current is induced? So actually the answer for that is that there is no current in that case. It is the electric field which is created. So that is another concept which is generally used in JEE Advanced. You don't have to worry about it right now over here. Chumma, they again try to show off over here. So the answer for this is that even though the circuit is open, yes, there is no current, but there is electric field which is created. The field will try to push, but it will have nothing to push because the circuit is incomplete. Only when the circuit is complete, the electric field is able to push the charges. So that is the answer for that. The motional EMF discussed can be argued independently from Faraday's law using this. However, even if the charges are stationary, you can still use this. Thus, moving charges in static field and static charges in a time varying magnetic field to be symmetrical situation for Faraday's law. This is a tantalizing hint on the relevance of the principles of relativity of Faraday's law. Now, the third point is basically a point of relative effects of motion on electric and magnetic fields. This part again I would say is a show off, because they say that when you change the frame of reference, the electric field can be perceived as magnetic field and magnetic field can be also perceived as electric field. So it's basically that, nothing else. So when you take a charge, stationary charge, it produces electric field around it. But the moment the charge begins to move, it is not only going to produce electric field, but also it behaves like a wire carrying current. It produces magnetic field. If the charge is stationary, you are moving. For you, the charge moves. So again, it will produce magnetic field. So that is what it is. It is basically the relevance of the principle of relativity in the Faraday's law. That's all. Okay. So even if you don't understand this third point, it's perfectly fine. Okay. So most of the pointers here in this particular chapter are pretty much useless, let me tell you that. Okay, so straight away move on. Don't waste your time. Don't break your head on, sir, what is this relativity effect? They'll never ask you such questions. Don't waste your time. Next. Alrighty. Let's see if we have something over here. Where is it? Yes, summary. Okay. Tomorrow session duration, I'll let you know. Sir, are you Malayali? Somebody saying, Salman is saying, sir is English. I don't know which state is that. Sir is English. Okay, chalo, let's see. AC. Guys, come on. Full Josh, full energy. Okay, what is this? This is so slow, no? See how and all it is behaving like one mental fellow only. Okay. Alternating voltage, AC voltage, it will be having one maximum value, Vm, and sine omega t term. Omega is the angular frequency. that is going to decide how quickly the direction of the AC current or the voltage will change. Now the current will also be maximum current into sine omega t, and the resistance will be current by resistance will be voltage by the current as given by this formula. Now when you purely have a resistor in the circuit, this is okay. Current is voltage divided by resistance. But when you have a resistor with a capacitor, or capacitor with an inductor, or inductor with capacitor with a resistor, why the hell is it acting like this? Then remember, the current and the voltage will not be changing together. Remember that they are not in the same phase. We'll come to that in a bit. But another important point is the RMS. Now what is this RMS? RMS is that current which produces the same power loss in the AC across the same resistor in the same time. See, in AC the voltage is increasing, decreasing, current is increasing, decreasing. So the power will also be increasing, decreasing. So what is that one value which will help me understand how much energy is there in that AC? So that one constant value which has the same energy as that of the AC is called as RMS, root mean square, and it is the maximum by root 2. 1 by root 2 is 0.707. You should know this. So you can use power is I square R, where I is basically your RMS current, not any other current. When you take an inductor, remember the voltage on the inductor is 90 degree ahead of the current in it. But when you take a capacitor, the voltage in the capacitor is below, current is here, so it is actually behind the current. If this is the current is ahead, the voltage is behind for a capacitor. Keep that in mind. Now, just like you have resistance, the resistance of an inductor is called inductive reactance. The resistance of a capacitor is called capacitive reactance. Inductive reactance is omega L, whereas capacitive reactance is 1 by omega C. These resistances do not cause any loss in power. Just like resistors cause heat loss, it's lost. But these resistances oppose the current, but they do not lose the energy. So they are a little bit good. You know, they are bad in a way that they oppose the current, but they are not so bad that they cause any loss. That's why we did not give them the same name of resistance. They are called reactances. When you have all the three elements together, then the total current is the total voltage divided by the total resistance of the circuit, often called as the impedance Z, which is root R square plus XL minus XC or XC minus XL. Don't ask me whether this comes first or this comes first, because anyways after subtracting or squaring it, so even if there is a minus sign, it gets eliminated. So it doesn't matter. And phi is the phase angle between the voltage and the current, because voltage on the inductor will be here, voltage on the resistor will be here, voltage on the capacitor will be here. When you find the vector resultant of all of them, that will be at an angle with respect to the current. So there will be a phase between the voltage and the current, my dear warriors. Now the power formula is not VI, remember it is V RMS, I RMS into cosine of the angle between the voltage and the current. So if you just write VI or VRMS into IRMS, that power is not the true power, that is called as the apparent power. That's not the true power, it is the apparent power. So the true power is VRMS IRMS cos phi. What is cos phi? Power factor. Power factor. So what is the maximum value of cos? 1. And when cos is 1, it is resonating. When cos is 1, it is resonating. The inductance and the capacitance cancel out each other. The circuit is purely resistive and the current is maximum. When you take a purely inductive or a capacitive circuit, cos phi is 0, power factor is 0, because inductor and capacitor do not cause any loss. They are good resistors without loss but opposing current. So that power loss is also called as the wattless current. The current which is flowing in them is called as the wattless current, and the power is called as the wattless power and all of that. Okay. Now, this point talks about phasor diagram. So if you know what a phasor diagram is, phasor is a representation of a time varying quantity like sine or cos. You would have studied this in 11th standard. A simple harmonic motion, an oscillating motion, can be converted into a circular motion whose shadow is basically the SHM. So the circular motion is called as a phasor. So when you have AC, where it is increasing, decreasing, positive, negative, you can think there is a rotating quantity which is producing this graph. So one thing is rotating and the other thing is producing this graph. So that rotating quantity is called as the phasor, and that diagram helps us to solve these AC problems like vectors. Otherwise, it would be very difficult to solve this using basic trigonometry. So phasor facilitates us to solve the problems by treating them like vector quantities. Next is transformer. What is a transformer? Transformer is going to change the voltage from low to high or high to low. High to low is step down, low to high is step up. A transformer is based on the principle of mutual induction. So when AC voltage goes through the primary coil, the current increases, decreases. Change in current, change in field, change in flux. That flux change passes through the other coil and produces AC voltage and AC current in the secondary coil through mutual induction. And there are some number of turns in the primary, some number of turns in the secondary. Primary is input, secondary is output. So the input voltage and the output voltage are related by this formula. Secondary by primary voltage is secondary by primary current turns. This is also called as the turns ratio, N2 by N1, turns ratio. Currents are exactly opposite. IS by IP is NP by NS. Unlike Vs by Vp is Ns by Np, current is Is by Ip is Np by Ns. This is only true for 100% efficient transformers, meaning transformers which do not cause losses. There are three kinds of losses in a transformer. One is basically your flux loss, where the flux gets lost in the surroundings and the energy is wasted. Second is basically the eddy current loss. So eddy current loops are produced in the core of the transformer. So you laminate the transformer to prevent the eddy current losses. The third is the hysteresis losses, which are due to constant magnetization, demagnetization of the core of the transformer. So you use a strong ferromagnet to reduce the hysteresis losses. So these are the three losses, and you generally minimize it to produce 100%, close to 100% efficiency. Remember that whenever you give the voltage, will they ask the definition? They can definitely ask you define capacitive reactance. So you will, or derive the value of it, 1 by omega C, right? Or derive omega L is equal to XL. So you have to start from the basics. Okay, so you need to know it, or they might just give you a 1 mark question, define it. You will give the units, you will write the formula, and you will tell that this is capacitive reactance, this is inductive reactance. You will have to write it. Okay, great. Moving on. Malini, I don't have the PDF of the derivation sessions for a deliberate reason, because there is no point only of the PDF. Even if you read it, even if I give it to you, it is waste. So I know something which is of waste is no point. You might feel good, sir, I got the PDF. You have to see it, you have to write it on your own. Only then it will enter your head. If you see me riding a bike, will you learn how to ride a bike? No, right? You have to sit on the bike, you will have to fall, you have to make mistakes, you will get hurt, then you will learn. It is the same way. You might feel bad, you might say, what is this, sir? One sir or one madam gave me, nice, beautiful handwriting sheets. Very good. All the best. Use those sheets. You will see tomorrow it will be utter waste. So that's the reason I will think about you. I know what is good, what is bad. I won't do things to make you happy. I won't just chumma do things to make you happy before the exam. I can make you extremely happy before the exam. I don't want you to do that. I want you to be happy during the result. I want you to be happy after the exam. You might find it to be extremely painful. You might find it to be, like, what is this, sir? Hard work I have to do. but that is what is going to give you results. That is what is going to give you marks. So you want it, please follow my method. That's all I would say. Yeah. Okay, let's go. Whenever voltages are given, generally they are given as RMS. You never get the peak or the average values. Like when I say 220 volts AC, it is RMS value. So if you want, you can find the peak by multiplying by root 2. That's the first point. Power rating of an element is used in AC circuits, refers to its average rating. Makes sense because instantaneous power will be 0, maximum, continuously varying. So average value is what is usually given to you. Both the power consumed in the AC circuit is never negative. Makes sense because power consumed. So power is always lost in that AC circuit. It is negative means what? I mean, power also, the formula is I squared R. I is the current, R is the resistance. So when you square something, it will always be positive. R is also positive. So power can't be negative. It's obvious. Okay. Both alternating current and direct current are measured in amperes, but how is ampere defined for AC current? It cannot be derived from the mutual attraction or etc. So the way currents units, amperes, were defined were by taking two wires parallel to each other and measuring the force between them and knowing the distance between them. Then you define for this distance this much force is there, then that current is 1 ampere. But for AC, how do you do it? That is the question. So an AC current changes the direction constantly. Thus, the AC ampere must be defined in terms of some property which is independent of the direction of current. So that's why you use something called as the Joule's heating property, and 1 ampere of RMS value of alternating current in a circuit if the current produces the same average heat as 1 ampere of current of DC. See, RMS is that binding factor. When you pass AC current continuously changes. How do you define 1 ampere of AC current, etc.? So what you do is you pass that current which produces the same heat in the same resistor in the same time as 1 ampere of DC current. So then that RMS current of AC is 1 ampere. So that's how it is defined in units in AC. That's all it says. Okay. In AC circuit, while adding voltages, one should take care of the phases. Yeah. Okay. So what this point, fifth point, means is that, see, usually in DC what happens, 5 volts plus 10 volts, you will say 15 volts. Fine. But in AC, 5 plus 10 may not be 15. 3 plus 4 may not be 7 because the voltages are not in sync. Meaning when one voltage is maximum in AC, the other voltage may not be maximum. Maybe it is 0, maybe it is minimum. So you need to take into account the phase. So the best way to do that is phasor diagram. And in phasor diagram, when you draw the voltages as phasors, you can treat them like vectors and add them like vectors and find the resultant vector. So that's how you find the resultant voltage. In AC, it's all about vector addition. In DC, it's all about scalar addition. That's the difference. If you realize this, good enough. Though in a phasor diagram, voltage, current are in vectors, these quantities are not vectors themselves. Yes, they are scalars. So it happens that the amplitudes and the phases. Okay, so this basically says that many people get confused, sir, how can voltages be a vector quantity? See, voltage is not a vector. The term, the simplification which you use, which is called as a phasor, that phasor diagram is a vector quantity. That phasors in that phasor diagram are vectors. So it's just a hypothetical imaginary quantity which helps us solve the problem in an easy way. That's it, nothing more than that. When you talk about AC, there are no losses with pure capacitances and inductance. The only element which causes loss is resistance. I have been telling this to you again and again. In AC, resistor is the only bad guy which not only opposes but also causes loss. Capacitor and inductor, they oppose but they don't cause any loss. Okay. Power factor is a measure of how close the circuit is to expanding to the maximum power. How close it is to expanding to the maximum power. Correct. So if the power factor is 1, that means it consumes lot of power, it delivers lot of power from the source to the circuit. If power factor is 0, whatever the source is giving, it is not absorbing only anything. If you talk about generators and motors, the roles of input and output are reversed. In a motor, energy electrically is converted into mechanical, whereas in generator, yes, mechanical is converted into electricity. Both devices transform from one energy to the other. Yes, perfect, makes sense. Transformer changes low voltage to high voltage. It does not violate the conservation energy principle. Many people think, sir, low voltage to high voltage, isn't it increasing the energy magically? No. What happens is you forget that the current reduces proportionally. So if voltage increases, current reduces, the product voltage into current, which is power, that remains constant. So energy principle is not violated. Is that clear? Very good. Let's move on to the next chapter. Let's go to EM waves quickly. This is a small one. Great. So, electromagnetic waves. Yep, we are on to electromagnetic waves summary, and I hope you guys are enjoying the session, you are loving the session, and you are revising things thoroughly. Although you might feel I have not studied many things, let me also tell you that there are some points which I am specifically mentioning. These are not important from board point of view. Chumma, they have given it for the sake of it. Other things which are important, I am discussing over here. So, Maxwell's laws are there in electromagnetic waves chapter first, and he saw that just like a current carrying wire can produce magnetic field, he also added that not just current can produce magnetic field, but even an electric field which changes can produce magnetic field around it. And that electric field which changes, that produces magnetic field around it, I can say it's just like an equivalent current which carries some current which produces magnetic field around it, and that equivalent current is called as the displacement current. So if you take a wire carrying current, it produces magnetic field. Some electric field which is passing and it is changing, and that is also producing magnetic field. Both are producing magnetic field. Here actual current, here some electric field. So that current which produces the same magnetic field as that of changing electric field, producing that magnetic field, that is your displacement current. The formula for displacement current is epsilon naught, which is permittivity, into rate of change of electrical flux. An accelerating charge produces EM waves. Electric charge oscillating harmonically with frequency f produces EM waves of the same frequency. An electric dipole is a basic source of electromagnetic waves. Correct. So, when you take a charge, it is at rest, it is going to produce only electrostatic field. But when the charge begins to accelerate, not only will it produce electric field, but also it produces magnetic field, and that too a changing electric magnetic field, which is then electromagnetic wave. In fact, electric dipole is a basic source of electromagnetic waves. So you take a positive and negative charge and you move them back and forth. So the dipole will keep on changing its length and its electric field around it, and that will change its magnetic field. So what you get around it is an electromagnetic wave. And such an device which produces an electromagnetic wave around it using a dipole is a dipole antenna. That's a dipole antenna which is there in many of your electromagnetic devices. EM waves with wavelength of the order of few meters were first produced by Hertz in 1887. That's a long time back. And he was able to predict whatever Maxwell said. That's crazy. Electromagnetic wave equation, everybody must know. E naught sine or cos 2 pi f, or omega t minus kx, omega t plus kx. Same thing, magnetic field is B naught sine or cos omega t plus or minus kx. Remember, E naught and B naught are the maximum electric and magnetic fields. So EM wave is where electric and magnetic fields are in perpendicular directions and they move like this. So if they are going here, if the EM wave is going here, electric field will be perpendicular to it, even magnetic field will be perpendicular to it, like snakes they will go. The ratio of electric and magnetic fields is the speed of electromagnetic wave, which is the speed of light. You can also see speed of the electromagnetic wave is 1 by mu naught epsilon naught, meaning if the medium changes, permeability and permittivity will change, so the speed will change. From that you can also measure the refractive index of the device. Great. Okay. The spectrum of EM waves stretches in principle over an infinite range of wavelengths. Different regions are known by different names: gamma, X-ray, ultraviolet. Okay, you should know all their uses and how they are produced also. There is a table in NCERT, there is a beautiful paragraph also in NCERT. Please go through all those things. Gamma rays is produced by nuclear reactions used in chemotherapy and treating cancer and tumors. X-rays produced by Coolidge tube and bombarding heavy particles on target elements, okay, heavy metals. And X-rays is used to detect bone fractures and fractures in different structures and all of that. Also to study the crystal lattice structure using Bragg's law of diffraction. Ultraviolet rays, how are they produced and how it is used to purify water and how it can be also dangerous for humans. Visible rays, what you can see and how it is produced by normal heating of bulbs and all of that. Infrared rays, microwaves, rays, radio waves, in the increasing order of wavelength, their uses, their application, their harmful effects if any, and how they are produced. All these things you should know. When you interact with matter via their electric and magnetic fields which set in oscillation charges and all the matters, the detailed interaction, okay, this is fine, there is nothing great over here. Okay, so when we talk about different electromagnetic waves like gamma rays, X-rays, infrared and all of this, many people think that they are actually different, but actually they are not. Actually they are not. They are only changing their frequency or wavelength, but everything is same. Their formulas are same. Their C is equal to F lambda. Their equations are same. Everything is same. Only the frequency changes, which produces different effects. Different penetrating power, different energy, different wavelength, different resonating factors. So many things could be different, how they affect different materials. So that's the only differentiating factor. Okay, rest other things are not so important over here. There is nothing over here. Okay. So here infrared rays, it's little bit mentioned over here. They are also called as heat waves because when you at a normal temperature, basically the body also emits electromagnetic radiation, and that radiation happens to fall in the infrared region. That is why it is also called as heat waves, meaning somebody is hot, they will emit more infrared, and if somebody is cold, they will emit less infrared region. So you can find out the temperature of a person, whether he has fever or not, measuring the infrared spectrum of that person. So it is also called as heat waves, also used in night vision goggles where nothing is seen, but if there is a person moving around using their infrared radiation which is falling onto the goggles, you can find out whether there is a person in the dark or not. The center of sensitivity of our eyes coincides with the center of the wavelength distribution of the sun, and this is because humans have evolved with vision sensitive to the strongest wavelength from the sun. So sun is yellow, or is it that because we can see yellow and colors around it, that's why I can see the sun is yellow? The answer is the first, because the sun is actually predominantly having many yellow wavelengths. That is why our life on the planet Earth evolved to see the sun and things which are getting affected by the sun, by the reflection of light from the sun. So that is why our eyes evolved to see yellow as a very sensitive color, and you saw few things here and there which is like orange, red, violet, blue, greens and all of that. So if the sun was infrared in color, then thousands and thousands of years back the evolution would have happened to see infrared as the primary sensitive color. That's all that is mentioned. Okay, great. Shall we go to the second part, or do you want to do it in the morning? 4 o'clock. What say? Let's do it. Just give me like 2 minutes break. We'll do it. Okay, just give me like 2-3 minutes break and then we'll start. Just 1 second. Yes, let's complete it now. Everybody ready? Get up, full of energy, full of josh. Had a small, short, little break, I believe. Let's begin. Let's begin. Let's begin. Get ready, guys. Let me just get my phone also so that I can see your chats. 1 second. Call up all your friends. Call up all your friends quickly. Part 1 is over. Get ready for part 2. Ray optics. Let's go to ray optics part 2 of your book, chapter 9 already. All right. Yes, there we go. Summary. Now, the law of reflection is purely governed by the equation angle of incidence is angle of reflection. So whatever angle at which the light falls in is the same angle at which the light reflects at, and the refraction law, meaning light going from one medium to the other, then the angle of incidence and the angle of refraction into the other medium, the sign of their angles ratio is a particular constant which depends on what is there on this medium, what is there on the other side of the medium. So it depends on the pair of the media. It's called as the refractive index. And the ray of normal, the ray of incidence, the ray of your reflection or refraction, all of them are in the same plane. It's not like incident is here, refracted is over there. No, it's all in the same plane. Then from the refraction concept, you get this total internal reflection concept, where you are in denser medium, the light goes to rare medium, the light bends away from the normal. But if the angle of incidence is beyond a certain limit, often called as the critical limit or the critical angle, then the light is not able to go to the rare medium. It will come back inside the denser medium itself, so it reflects. It follows all the laws of reflection also. That is called as total internal reflection, and the sign of that critical angle is 1 by the refractive index of the medium. Diamond shining, the optical fiber network, the way it operates, so many, even mirages, all these examples and phenomena are based on the concept of total internal reflection. The concept of optical fiber, all these phenomena, you should study it in detail. You might get specific application based questions also in your board examinations. Cartesian sign convention. This sign convention is useful because your object distance, image distance, focal length, radius of curvature, all these things, yeah, are completely dependent on the signs. They are not distances, they are coordinates, they are having some signs. All of this is decided by the Cartesian sign convention, where upwards is positive, downwards is negative. The direction of the incident light is positive, opposite to the incident light is negative. So all the things are measured as per the incident light's direction. Keep that in mind. Mirror equation gives you where the object is if the image is here, or where the image is if the object is here, or if you know where the object and image are, you can also find the focal length. 1 by V, 1 by U is 1 by F. Now the focal length of a concave or a convex mirror is given by or related to its radius of curvature. Radius of curvature is the radius of the curved mirror, of which it is of the sphere whose part that mirror is. That radius is related to the focal length as r is equal to 2f. R is equal to 2f. If the focal length is negative, it's a concave mirror. If it's convex, the focal length is positive. Okay, keep this in mind. Then prism. Let's talk about prism because you go to refraction. Prism has many geometrical aspects like angle of prism, internal angles R1, R2, angle of deviation, which is I1 plus I2 minus A, then R1 plus R2 is equal to A. The deviation depends on the angle of incidence, and at a particular angle, when the incident angle I1 and the emergent angle I2 are equal, the deviation is minimum. And when such minimum deviation occurs, the refractive index is given by sine A plus delta minimum by 2 by sine A by 2. Also, you should know, for a curved surface, when the light refracts, the object forms an image somewhere. The formula to find the image is given by refractive index of the second material by image distance minus mu1 by u is equal to n2 minus n1 by r. R is the radius of curvature. Using this, for a single curved surface, you add two surfaces together, it becomes a lens, and you get the formula for the focal length of a lens, also called as the lens maker formula, which is refractive index minus 1 upon 1 by r1 minus 1 by r2. What is r1 and r2? Is the radius of curvature of both the surfaces. Lens formula is nothing but 1 by v minus 1 by u is equal to 1 by f, exactly opposite of the mirror formula. Great. Now when you take multiple lenses and put them together, it behaves like a one single lens, and you do not add the focal length. In fact, you add the power of the lens. In fact, the power of a lens is 1 by f. F, if it is in meters only, then you measure the power in diopters. Many students forget to convert focal length in centimeters to meters. You might lose marks there. 1 by f1 plus 1 by f2 plus 1 by f3 is 1 by f. F is the effective focal length. Just like you add p is equal to p1 plus p2 plus p3, because p is 1 by f. Powers add, focal lengths do not add. Dispersion is where your light gets split into individual colors, because each color has its own different refractive index, because of which the angle of refraction, the angle by which it deviates, is also different. Keep that in mind. So because of the different refractive index for different colors, you will see the light will split into different constituent colors. Next comes the optical instruments part, where you have something called as the least distance of distinct vision. Your eye is an adjustable focal length. It can focus on infinity, it can focus on close things also. But you can't bring close too close, because then the eye gets strained beyond a certain limit. It is not able to accommodate its focal length. So the least distance till which it can see clearly is D. For an average adult, it is 25 centimeters. That is also called as the near point. The far point is the farthest distance till which it can focus. For a normal human, it is infinity. Now, if you use a normal magnifying glass, then if you place the object in such a way that the image is formed at the least distance of distinct vision, that means as close as possible, you produce a magnified image, and the magnifying power is 1 plus d, which is 25 centimeters by the focal length of that lens. But if you make that image at very far away distance, then that 1 will not come, it is just d by f. That's the magnifying power. Similarly, if you use a combination of two convex lenses, it becomes a compound microscope, and for a compound microscope, the magnifying power which is there is the length of the microscope, meaning from one lens to other lens, what's the distance, that's the length, upon focal length of the objective. Objective is that lens which is closer to the object. It's a small lens, so it is FO into D. D is 25 centimeters, that's the least distance of distinct vision, upon focal length of the eyepiece. Eyepiece is the lens through which you see. Okay, so there are two sides of that microscope. Okay, next, magnifying power of a telescope. Telescope is used to see far away objects in a magnified manner. You will see the objective is very huge, the eyepiece is very small for a telescope. Objective is huge to prevent the undesirable effects of diffraction, and also to improve the intensity of the light which is going to focus to form the image. The magnification formula is simply focal length of objective upon FE, focal length of the eyepiece. Also, if you add FO and FE, you will directly get the length of the tube of the telescope. As simple as that. Keep these things in mind. Okay, moving ahead, points to ponder. Reflection and refraction are true for all the surfaces. Yes, it's not like it is only true for flat surface. Even if you take a curved surface will also have small flat surfaces. So it's true everywhere. The real image of an object between f and 2f of a convex lens can be seen on a screen. If the screen is removed, is the image still there? The answer is very interesting because this question puzzles many people. Now, if you think about a real image being formed at a place, then you say that the real image can be obtained on a screen. But if the screen is not there, then can you still see the image? The answer is the image is still there, but can you see it? The rays from a given point on the object are still converging to an image point in the space and diverging away. The screen simply diffuses these rays, some of which reach our eye, and we see the image. This can be seen by the images formed in air during a laser show. So, although a screen is used to see the image formed by a lens or a mirror, okay, which is real in nature, then if you do not have the screen, then what happens is the rays converge and they end up again diverging. And when they, after converging, because they again end up diverging, and then again when they reach our eyes feel that, oh, the rays are coming from this point. So the image is still there, whether the screen is there or not. The presence of the screen only makes it clearer to our eye, else our eye will perceive, oh, there is an image over here and not somewhere else. Image which is formed needs regular refraction. All the rays from a given point should reach the same point. This is why you should not see your image by an irregular reflecting object, say the page of your book. So basically what they say is to form a distinct clear image, not only two rays, multiple rays should meet at the same point, else what will happen? Any random rays will meet at random places, so the image will not be clear, it will be hazy. So ensure that your reflecting or refracting surface is proper, which ensures a crisp, clear image is formed. Thick lenses often give you colored images due to dispersion. The variety in colors of objects we see around us is due to the many colors which our light around us have. A monochromatic light will produce a very different perception about colors of an object as seen whether in white light. Because monochromatic wavelength has only one single wavelength, so the ray diagram will look very different than white light. White light will have many colors, so each color will meet at a different point, and the way you perceive the object's image will be way different than a single color image which is formed by an object. That's what it says. It's only because of dispersion, which is different mu due to different wavelength. If you talk about a simple microscope, the angular size of an object equals the angular size of an image, yet it offers magnification because we can keep a small object much closer to the eye than 25 centimeters and hence have the subtend larger angle. The image is at 25 centimeters, which you can see without the microscope, which you would need to keep the small object at 25 centimeters, you would make subtend a very small angle. See, what it means is, if I take this pen, okay, this is an object, if I keep it close enough, it subtends an angle, I see it big. If I keep it far, it looks small because it subtends a small angle. I can't keep it very close because it will fall beyond or below my least distance of distant vision. My eyes will not be able to focus on it clearly. When I have a magnifying glass, then it magnifies it in such a way that even if the angle is same or whatever, it ensures that the image is beyond my least distance of distant vision so that I can see it clearly. Eye is able to focus and it subtends a large angle at my eye. So thus it produces a sensation as if the object's image has been magnified. Okay, so that was with regards to points to ponder. Let's go to the next thing. Wave optics. Okay. One of the first pointers in summary of wave optics is that about Huygens principle. Yes, Jeevan, this question came in PYQ. That's why you should read all these pointers, because you don't know tomorrow what is going to come. Harsha, Sai, Tamil, glad you joined at least here. Whatever parts you have missed, make sure you watch the recording. All the students who are joining in late, don't think, oh my god sir, I missed so much of the class. What to do now? Where should I watch it? Don't worry, after the session is over, the entire recording is going to be there on YouTube. So watch it. But for now, continue with the live session. Doesn't matter. You don't have to go chapter 1, chapter 2, chapter 3. If you have started now from here, continue. Watch the remaining parts later. Huygens principle tells us that each point on a wavefront is a source of secondary waves which add up to give a wavefront at a later time. When you drop a stone in water, it produces waves. Okay, now imagine you drop some 10-15 stones in water, it will produce so many waves, they interfere and produce a new wave. So what Huygens said is, when you turn on a light bulb, it produces waves around you, and that waves disturb new points in the medium which act like new sources called as secondary sources. They generate new waves which interfere and produce new waves called as secondary waves. And that in turn produces new tertiary sources producing tertiary waves and then producing tertiary wavefront. Huygens construction is exactly that. So when the speed of the light is independent of the direction, the secondary waves are spherical, the rays are perpendicular to both the wavefronts and the time of travel, and the principle leads to the well-known laws of reflection and refraction. So using Huygens construction, whatever I just told you, primary creating secondary source creating secondary waves, the common interference tangent producing the new wavefront. Using that simple principle, you can prove law of reflection as well as refraction. I have done that in the derivations class. Please watch it. It's there on this channel itself. Next thing is that also remember, the ray of light is always perpendicular to the wavefront. This might remind you of field being perpendicular to equipotential surface. If field goes from high to low voltage, the equipotential surface is perpendicular. Same way, if the ray of light goes like this, the wavefront is perpendicular. Wavefront is all those points in the medium where the rays reach at the same time. All these points are disturbed simultaneously. That is basically a wavefront. The principle of superposition of waves applies whether two or more sources of light illuminate the same point. When we consider the light's intensity, at this point there is an interference term in addition to the sum of the individual intensities, but this term is important only if it has non-zero average, which occurs only if the sources have the same frequency and a stable phase difference. Now the superposition, applies. Superposition means what? If one light bulb is turned on, other light bulb is turned on, third light bulb is turned on, all these light bulbs, light waves come and meet at a point, you will get a new light intensity, and that light's intensity depends on how far these light bulbs are, how intense these light bulbs are, where are they meeting, and all such things. Now when these interference patterns occurs, or when this interference occurs, this superposition occurs, so that new intensity, all right, is having or you can get that formula by a vector addition of their amplitudes. Vector addition. So what is vector addition of their amplitudes? You think of light waves as sinusoidal waves. Just like in AC, voltages can be treated like vectors in phasor diagram, and you add to find the resultant voltage. Same way, you add the light waves amplitudes to find the resultant amplitude. From that you get the resultant intensity. That's how it works. Okay, in YDSC setup, the slit separation D gives equal spaced interference fringes, correct? So YDSC, when you take two slits in a cardboard piece and behind that there is a light source, each of these slits behaves like a coherent, that means in sync source, which produce new wavefronts, and these wavefronts interfere somewhere constructively, somewhere destructively, somewhere constructively, somewhere destructively. So you see alternate bright dark fringes on the screen, and these fringes are equally spaced. The fringe width is given by lambda d by small d. For a single slit diffraction pattern, you have a maxima and the intensity keeps on falling. Diffraction is where the light spreads as it passes through a small hole or an aperture. Interference is where multiple light sources meet at a point to produce resultant wave. Diffraction is where the light spreads when it passes through a corner or a hole or an aperture. That also produces interference, but it is slightly different in the sense the alternate bright and dark fringe slowly becomes faint and faint and faint, and slowly after 2-3 bright dark fringes you can hardly see anything. That's the main difference for a diffraction pattern. Natural light, that is from the sun, is unpolarized. This means the vector takes all possible directions. Polaroid transmits only one component parallel to the special axis. The resulting light is called linearly polarized or plane polarized. When this kind of light is viewed through a secondary Polaroid, whose axis turns to 2 pi, 2 maxima and minima occur. See, our natural light which is produced, no, I didn't have my dinner, my dear warriors. Okay, I will have my dinner only after this session is over. Okay, so I have just come over here only for all of you because I had to take this marathon. I have driven all the way around only for all of you. So make sure you are not only attending the class but also supporting the channel by liking and also commenting after the video ends. I want to see all the comments or the attendance. I want to know all the students whether you are live or recorded. Okay, and share this video friends too in your groups, WhatsApp, Instagram, wherever. Okay, or just talk about this channel. Okay. Talking about natural light or the light produced by even a normal bulb, it is unpolarized, meaning the electromagnetic waves, the electric field is once here, once here, once here, once here, once there. It's in all the directions. It's unpolarized. There is no unique direction. But when such a light passes through a polarizer or a polaroid, only a particular component of the electric field passes. The remaining components get eliminated. So when light has only oscillations in one direction, it is a polarized light. And that happens when it passes through a polarizer. Now, when I have a polarized light and I use another polarizer after it, and it so happens that both the polarizer plane and I see the light's plane are aligned properly, then I can see it properly because all the light will pass on to the other side. But imagine if I tilt the polarizer, then I will slowly see the intensity reduce and it will vanish at 90 degree. Again, it will become maximum. Again it will vanish at 90 degree and again it will come. So in one complete revolution, I will see minima, maxima, minima, maxima. So 2 maximas, 2 minimas is what I will see if I rotate the second polarizer. That is what it is saying. Okay. Waves from a point source spread out in all the directions. When light was seen to travel along narrow rays, it required the insight and experiment of Huygens, Young and Fresnel to understand how a wave theory could explain all aspects of the behavior of light. Okay. So basically this is again historical. There is nothing great about this point. Waves from a point source spread out in all the directions while light was seen to travel along narrow rays. Basically in those times people used to think that light travels in straight lines. Okay, so they had to explain how light is able to spread out, how light is able to go in different directions and all of that. So it took Huygens, Young and Fresnel, all these were saying that light is a wave. Newton said light is a particle. So all these scientists were involved in wave theory. The crucial new feature of waves is interference of amplitudes from different sources, which can be constructive, destructive, as shown in Young's experiment. So what is the difference between a wave and a particle? Particles can never interfere. They can collide, transfer the momentum. But a wave, when they collide, actually they don't collide, when they meet, then they interfere and they add their effects. It's not like they rebound back. Okay, the waves do not reflect back like that. They will add and continue moving ahead. So that is the main thing about light. And if the crests meet together, troughs meet together, it is constructive. If crest and trough and crest meet together, it is destructive. That's what it said. And that's what Young's double slit experiment was able to show, that light also can interfere. Okay? Yes, very good. Now, diffraction phenomena defines the limits of ray optics, the limit of an object's ability to microscope, telescope to distinguish very close, etc. Okay. Now, diffraction, like I said, when light passes through narrow slit, it spreads. If the slit's width is changed accordingly, the spreading angle also changes. If it is very narrow, it spreads a lot. If it is wide, then it spreads a little bit less. So that was used to make different optical instruments. So if you make a very small lens, then the light might spread, the light might get completely diffused, and you might not get a crisp image. So this phenomenon of diffraction is used to design optical instruments so that you get crisp, clear images. Also particularly useful to see distant stars and planets. If the light from a star or a planet passes through the lens's aperture, which is also a hole at the end of the day, if it spreads like that, you will not get a clear crystal image. So that is what is very important. That's why you use a big aperture, so that the diffraction effects are very minimal. You see a clearly resolved image. Many interference and diffraction effects exist even for longitudinal waves like sound in air, but polarization phenomena are special to transverse waves. See, interference, diffraction, these happen not just for light, but also happens for sound, happens for in fact any wave. Any wave has interference and diffraction phenomena. But this effect of polarization is only for transverse wave, like wave on a string or light waves. Sound cannot be polarized. Sound is a longitudinal wave. Keep this in mind. Okay, so that was your exercise. Let's move on to the next chapter coming up on your screen now. Ready for the last four? Ready for the last four? Dual nature. We have already entered modern physics, my dear warriors. Yes. Bharat, 10 finished, 4 remaining. How many of you are there from the beginning? Put it up on the chat box. Put it up on the chat box. Always, always. Thank you, Krishna, for attending both. Kim, I did not have my dinner. I hope you had yours. Or tell me if you are like me, supporting me by not having dinner. Don't even ask, I'm very, very sleepy. Extremely sleepy, because I have just hardly slept for any time from the last 2-3 days, and I have been driving for, like I told you, some 800-900 kilometers. Yeah. Yesterday also I took class, today also. But yeah, it's your exam tomorrow, so how can I sleep? It will not be right. Very good. Nice to see all of you. Awesome. Awesome. Let's move on to the next one, next one coming up on your screen. Here it is. Okay, I hope the text is visible. Not sure, because on the mobile screen it might look a little bit small, but it's okay. Hopefully we'll be able to zoom. Okay, the minimum energy needed by an electron. We have come to dual nature. This is the third chapter in the second physics book. Okay, right. The minimum energy needed by an electron to come out of a metal surface is called the work function. Like if you want to call your friend out of the home, you need some minimum energy, minimum amount of work to bring him outside, else he won't get permission. So that is exactly needed by an electron to come out of its house, called as the atom. That is called as a work function. It depends from metal to metal. Each electron might be let go of easily or with little bit more difficulty. Accordingly, work function will be higher or lesser. Now, if the energy of the light or the photon which is falling onto the metal is higher than the work function, that is the minimum energy, then the electron will be plucked out. Then you will see the photoelectric effect happening, meaning the photo is photon of light is falling and electron is being ejected out, else photoelectric effect will not occur. Okay, the other ways of creating electrons out of metallic surface or any surface is basically, one is called thermal or thermionic emission, where you heat up the metal surface. So because of the random collisions, the electrons get thrown out, knocked out. That is the second way. One is photoelectric, second is thermionic, by thermal energy. Third is field emission. Field emission means you create a strong electric field. That electric field is so strong that it plucks out that electron by the strong electrical force and the electrical discharge occurs. Best example is lightning. such a strong electric field is there, the charges from the clouds or the earth get pulled apart and you will see electricity flowing even in a non-conductor like air. Photoelectric effect, okay, yeah. Okay, photoelectric effect is the phenomena of emission of electrons by metals when illuminated by light of suitable frequency. That's the definition. Certain respond to UV, certain respond to visible, certain might respond to even infrared. That obviously depends on the material. This effect involves conversion of light energy into electrical energy. It follows the law of conservation of energy. Makes sense, because light energy is converted into electrons energy, and this is an instantaneous process and possesses certain special features. What are those special features? You have seen in the complete chapter, like the current depends on the intensity, stopping potential is independent of the intensity, right? So many graphs are there, slopes of stopping potential versus your frequency, which is incident, which is constant, right? So all these are special parameters or features of photoelectric effect. This photoelectric current depends on the intensity of light, potential difference, and the nature of the material. Makes sense. If the light's energy intensity is more, then more photons will come, more electrons will come out. So hence intensity. Second, potential difference. When the electrons come out, if there is a good voltage after it, that voltage might help or prevent the electrons from accelerating or decelerating further. So the current might automatically increase or decrease. Third, the nature of the material. Maybe you are using the same intensity of light, maybe the same voltage is used, but if the material does not let go of the electrons easily, then it might be a little bit difficult to get such good current. But if the material lets go of the electrons easily, lower work function, so you might see a slightly improved value of the current. Next, the stopping potential depends on the frequency of the light, the nature of the material. Why? Once the electron is emitted out, if it is decelerated, that means by the time it reaches the other side, you stop it and it goes back and falls onto the plate. So that voltage required to stop it is called as the stopping potential. So what will it depend on? Obviously, the speed of the electron. If the electron is coming out with large speed, you need a strong voltage to decelerate it, stop it and take it back. So what will the speed of the electron depend on? The kinetic energy. It will depend on two things. One is the frequency of the light. Second is the material. Why frequency of the light? If the light which is falling is of higher frequency, HF, F is more, HF is more, energy of the photon is more, the electron's energy is also more. Second, the commission that you are giving, some energy is always taken out by the atom to pluck it out. So if it takes out a lot of energy, the kinetic energy remaining will be less. So automatically the stopping potential will be less. That's why. So that's why E into stopping potential is the value of the kinetic energy of the electron which comes out. Below a certain frequency, no photoelectric effect occurs. We just discussed this because below a certain frequency, the photon's energy is only so less that it can't even pluck out that electron. So basically the friend's house which you went to ask the friend to join you for a dinner or lunch or for some party, that friend did not come out because you are not very persuasive. You are not convincing enough to the parents. The parents thought he is going to spoil my kid. That's why they shooed you away. So you need to be really convincing to, get your friend outside the house. All right. The classical wave theory could not explain the main features, etc. Einstein explained these features. Okay. So this particular initial part talks about how light was assumed to be a wave, and whenever people thought of light as a wave, they thought of continuous light energy being passed on. But Einstein said no, light's energy is not very continuous. It comes in packets, and in fact Planck's constant gave that energy value also, HF formula. So Einstein won the Nobel Prize also for photoelectric effect to prove that light is not a wave, it is a particle. And he explained these features using the photoelectric equation. Particle has special characteristics, like it has momentum, it can collide, it can be felt when it hits the surface, it imparts some force, some pressure when it hits the surface. All these things were experienced and explained very well by Einstein, Planck and so many others back then. The momentum of the particle of light is h by lambda. The particle of light is called as photon. What is lambda? The wavelength of light. What is p? Momentum. Yes, light also has momentum. Got it? Okay. Einstein's photoelectric equation. Einstein's photoelectric equation is right over here. Okay. In fact, you can take phi on the other side. So hf is the energy of the photon. Hf is the energy of the photon will be the energy of the photon which is falling onto it will be equal to work function. That means the energy required to pluck out the electron. That is number one, plus half mv square. That means the remaining part will be the kinetic energy. So if the photon gives 100 joules of energy, maybe 20 joules is just needed to pluck it out. Remaining 80 joules will be in the form of kinetic energy. So the kinetic energy is the energy of the photon minus the energy which is needed to pluck it out of the metal. Now, radiation has dual nature, wave and particle. The nature of experiment determines whether it is wave or particle. Okay. So, Victor de Broglie attributed wave-like character to matter called as matter particles. The waves associated with them are called matter waves. Okay. So, see, when we say light is a wave or a particle, people think, what do you mean by this, sir? Is light a wave or a particle? You tell me a final answer. The answer depends on whether you are conducting an experiment this way or that way. Some experiments tell you light is a wave, some experiments tell you light is a particle. So depending on the experiment, your light will show either this or that behavior. So it is crazy to think about it. Okay, so it is crazy to think about it that the experiment determines whether it is a wave or a particle. Very good, very good. Yeah. Siddharth, you can do one thing. You can watch my old AC class if you want one shot. Zero to hero, zero to superhero. Just search for it on YouTube. You will get it. A beautiful lecture to understand all the concepts of AC. And I would suggest AC is one chapter which you must study from me, because AC is a chapter which can be completely taught by vectors and phasors and all of that. And many people teach it using formulas, but actually it's a chapter just to be dealt with vectors. So please learn from me. It's there right on YouTube. Okay, cool. Moving on. The wave associated with moving particles. Okay, so like I said, the experiment determines whether it's a wave or a particle. Second thing is, de Broglie thought that if light can show particle and wave behavior both, then even mass like me, the book, the table, the fan, etc., stone, that is a mass, that is a particle, that can also have wave-like behavior. That wave is called as matter wave. And he found and established, yes, there is a matter wave associated with mass, and the lambda of that matter wave is h by p. Wavelength is h by p. That is also called as the de Broglie wavelength. But usually the momentum is so huge, the wavelength is so small, it is very difficult to detect the matter waves around everyday objects. Okay, all these are normal things. Now, free electrons in a metal are free in the space, free in the sense that they move inside the metal in constant potential. They are not free to move outside the metal. Okay. Now, a lot of people often ask this, sir, you said that in conductors there are free electrons, so why can't you just pluck it out? So they are free from the atom in the conduction band, but they can't be free from the solid. So they still have to get out of that solid. Understand that? Just like you might be free to move inside the house, but you might not be free to get out of the house. So when I say it's a conductor, maybe it can just move around in the house. It's free, but it can't go out of the house. So to get it out of the house, you need minimum work function amount of energy. Free electrons in a metal do not have all the same energy like molecules of a gas jar. The distribution differs like Maxwell distribution. You will learn in later courses, but the difference has to do with the fact that electrons obey Pauli's exclusion principle. Why did they have to make this point? It is a completely useless point for this level. They just said that, all the electrons do not need the same energy, just like the molecules of a gas in kinetic theory of gases. Some have more, some have less. So on an average, you need some amount of energy to take out these electrons. So they have said it includes Pauli's exclusion principle, and you will study it later. I mean, to make a point, I could have made any other random point also, saying some fancy words saying you will learn this later on in engineering, it is very fancy. This is not going to be asked in exam. Why chumma confuse kids? This is useless. Don't worry. Because of the energy distribution of the free electrons, energy required by an electron to come out of the metal is different for different. Okay, this is the same thing. Don't worry about it. Okay, observations on the photoelectric effect imply that in the event of matter-light interaction, absorption of energy takes place in discrete units. This is not quite saying as light consists of particles each of okay. So observations on the effect, photoelectric effect, imply that in the event of interaction of light, energy takes place in discrete units. It is not the same as saying light consists of particles each of energy h f or h nu. Meaning, see, whatever energy interactions are happening, you know, when lights, photons collide with the electrons, with the atoms and all of that, always they are in integral multiples of hf, just like charge is quantized, right? So you will have n times of E. Same way it will be either hf, 2hf, 5hf, 10hf, like that. So that is what they are saying. It is in a kind of way like it is discrete in the units of hf or h nu. So all the multiples of hf is the levels at which the energy interactions occur. Keep that in mind. Observations on the stopping potential are crucial discriminator between the wave picture and photon picture of photoelectric effect. Okay, so they say that how did Einstein for sure say that light is a particle and not a wave? Was the idea of the stopping potentials dependence on frequency and not depending on intensity, because when you increase the intensity of light also, if photoelectric effect is not occurring, it will still not occur. If light were to be a proper wave alone, then when you increase the intensity, the energy of the photon will or the wave will increase. So the electron will eventually be coming out. But that was not the case. Light behaved like a particle in that experiment, and only if the particle of light had more energy, then only photoelectric effect occurred. When you increase the intensity, it's not that the photon's energy increases, it's just that the number of photons increase. Still, each energy of the photon is the same. So if it is not able to pluck out an electron someplace, no other photon can pluck out the electron. So nowhere will you see the electrons coming out, and photoelectric effect will not occur just because intensity has increased. Only when you increase the frequency, they saw that the photoelectric effect occurred. So that was a crucial differentiating factor. That's what they say. Wavelength is given by h by p, has physical significance. Its phase velocity Vp has no physical significance. However, the group velocity of the matter wave is physically useless points to ponder. Don't worry about it. Phase velocity and all that, why do you have to? It's not there. Chumma, they have put high level stuff over here to show off. Ignore. Okay, so whatever Shreyas Sir says, just study that. Unnecessary things, don't break your head over it. Moving on. Next, chapter 12, atoms. Ready for atoms? Okay. Yes, I'll drink some water. The derivation of reflection at a physical surface can be asked. So if it is there, please do it. If you can do it right now, please do it. It is not going to take you much of time. Usually I feel that derivation might be given with an option, because not many people are going to do that. But lens maker derivation, prism derivation, those are important in ray optics. It's all according to the new text, Ram. It's all according to the new variations, okay? Fine. So summary of the next chapter, the fourth chapter in your second physics book of atoms. Okay. Atom as a whole is electrically neutral, therefore contains equal amount of positive and negative charges. That's what even Thomson said, and most of the other scientists, that say atom is neutral. It has no net charge. There is some positive charge by the protons and negative charge by the electrons. Standard. Thomson's model is not so important, but yeah, anyways, you can study. An atom is spherical cloud of positive charges with electrons embedded in it. So Thomson's model was a cake pudding model or a watermelon model with a negative charge as the positive, with the negative charge being distributed and the positive charge being distributed and the negative charge like the seeds of the watermelon. Okay, so the negative charge was like the seeds of the watermelon, and the positive charge was distributed like that red part of the watermelon. All right. Rutherford's model was where the most of the mass of the atom and its positive charge was concentrated in a small space. So he said, unlike Thomson, who said the charges are distributed, scattered across everywhere, he said no, the positive charge is not scattered across like the red part of the watermelon. It's at a very small point, and it's the point where most of the mass of the atom is concentrated. The electrons have negligible mass, and he derived that using the scattering experiment using a foil. And he said that the electrons revolve around it. Rutherford nuclear model has two main difficulties. So each model will have its plus and minus. So please make notes of that as well. You might get as 1 mark or 2 mark question. Problem was, it predicts atoms are unstable because the charges are accelerated. So they should emit radiation and fall into the nucleus. He was not able to explain that. Second thing, he was not able to explain the atomic spectra. Why does this atomic spectra come? So that difficulties were overcome by Bohr. Atoms are stable, they emit spectrum, and they are a set of parallel lines termed as line spectrum, and that is like a signature. Each element has its own unique line spectrum and emits those wavelengths, and that is very unique to that element. And also, atoms are stable, the electron continuously revolves, it does not emit radiation such that it the electron collapses into the nucleus and the atom explodes off. No, atoms are stable. So these were explained by Bohr, and he proposed a new model where the electron revolves in stable orbits called as stationary orbits. The electric force provided the necessary centripetal force for the circular motion, and the angular momentum, if it is n, h is Planck's constant by 2 pi, and n is the principal quantum number. For K shell it is 1, for L shell it is 2, and so on and so forth. Then the atom's electrons are in a stable orbit, and only in these stable orbits the electrons can exist and revolve, otherwise it will collapse. Next, the third postulate says that the electron might take a transition, so meaning the electron can jump from a lower orbit to a higher orbit, and when it makes that jump, it has to absorb a photon of the exact same energy of the energy difference. If it jumps from higher to lower energy, it must emit a photon of the exact same energy difference between the two orbits. Not just that, using that he was able to derive the radius, energy, speed, etc. of the electrons, and that was very accurate till certain limits. So like radius was proportional to n square, energy was inversely proportional to n square, velocity was inversely proportional to n, and so on and so forth. These formulas are very, very important, n being the principal quantum number. And when you put for hydrogen atom n is equal to 1, meaning the electron is in the ground state, the energy that you get is minus 13.6 electron volt. So that is the energy of an electron in the ground state of a hydrogen atom. If you give the or make the energy 0, meaning the energy is such that it makes the electron completely free. These energies are negative, meaning the electron is bounded to the atom. That's why sometimes it is also called as binding energy. So whenever energies are negative, it is bounded, it is positive, it is unbounded, it is completely free. It's 0, that means it is just free. So to pluck out an electron from the ground state and just remove it from the hydrogen atom, you would need 13.6 electron volt. and that is also going to ionize because the hydrogen will be at a complete loss of an electron. It will become positively charged, it will become a cation, so it will become ionized. So 13.6 electron volts will also become the ionization energy of hydrogen. De Broglie hypothesis says that electrons having wavelength h by mb gave an explanation of Bohr's quantized orbits. By bringing in the wave-particle duality, the orbits correspond to statical standing waves in which the circumference equals to the whole number of the wavelengths. So De Broglie and Bohr's hypothesis go hand in hand with each other, and it was also proved that if the electrons have some momentum mv, so they will have some De Broglie wavelength. Those wavelengths produce a standing wave. Standing wave, remember, waves which are going in opposite direction interfere with each other, produce a standing wave, nodes, antinodes. And that standing wave means that the energy is neither going that way or this way, it is stationary. So that stationary wave creates the sense of stationary orbits where the energy of the electron can't be lost in the form of electromagnetic waves. So it was in complete sync, and that explained the shortcomings of Rutherford's model. Bohr's model is only applicable to hydrogen single electron atoms. It can't be even explained for double electron atoms, or that is one major drawback. Not just that, it was unable to explain the relative intensities of the frequencies emitted even by hydrogen atoms. In fact, even small variations were there in the radius and the energies. It was unable to also explain something called as the Zeeman effect. All that you need to know is that Zeeman effect is when you put electromagnetic fields into the atomic spectra, the spectral lines split. That splitting of the spectral lines is called as the Zeeman effect. Why does this happen? He was not able to explain. So these were the major drawbacks of Bohr. Another main drawback of Bohr was he was able to predict the radius as well as the velocity, meaning the position and the momentum simultaneously, which violates Heisenberg's uncertainty principle. Okay, so all these were shortcomings. In the points to ponder, Thomson as well as Rutherford's are unstable. Thomson's model is unstable electrostatically, while Rutherford's model is unstable because of electromagnetic radiation. So basically they say that Thomson and Rutherford were students who gave failed theories, but Bohr's model was much better. Why did they fail? Because Thomson's model was not electrically stable. How can electrons be like seeds in a positive sea of charges? How is it even stable like that? I mean, how will they not get pulled and collapse into each other or repel each other? And Rutherford's problem was, how is the electron not losing out electromagnetic radiation? What made Bohr angular momentum and quantize it and not any other thing? H has dimensions of angular momentum, and for circular orbits angular momentum is a very relevant quantity. The second postulate is then so natural. So basically this second postulate of L is NH by 2 phi actually comes from the fact of stationary waves being produced in a orbit where the energy is not lost. So that is a more detailed discussion. Don't break your head over it. Okay, don't break your head on the second pointer. Orbital picture in Bohr's model of the hydrogen atom was inconsistent with uncertainty. It was replaced with, I just told you, Bohr's model had a shortcoming that it did not obey Heisenberg's uncertainty principle. Always there is a chance of finding something. If you find something, you don't know the momentum. If you know the momentum, you don't know where it is. So that's why you have a new theory, the modern theory, where you have the electron orbital theory, where it is all about probabilities of finding something. Okay, this you ignore. Basically this is about the planetary model of the sun, with the sun at the center and the planets going around it. Can be it's very similar to the nucleus at the center and the electrons going around it. Very similar. Here there is electric force, there it was gravitational force. But in electrons orbiting the nucleus, only certain orbits are allowed. But in planets going around the sun, all the orbits are allowed. There is no such restriction over there, right? Bohr laid the foundation of quantum theory by giving that certain orbits will not radiate energy where the electrons are there. Bohr's model includes only one quantum number, the new theory called as the quantum mechanics. Okay, this is all not required, don't worry about it. All these L, M, N, all those sub-quantum states not required for physics. Bohr's semi-classical model also not required. No, this and all is not required. So don't waste your time here. Okay, moving on to 205. Moving on to 205. Nucleus. Kept an alarm for the 3:30 class. Thank you so much. When they give you the efficiency of a transformer, what you do is basically see, you know the input voltage, you know the input current. Voltage into current is power. Let's say the efficiency is, example, 80%. So 80% of the input power is the output power. So V1 I1, input power is V1 I1 into 80%. That means 8 by 10 or 80 by 100 will be output power. So that will be equal to V2 I2. So you can find V2. How do you find V2? By turns ratio. N1 by N2 is V1 by V2. N1 you know, N2 you know, V1 you know, V2 you can find out. Once you know V2, you can find I2. That's all. That's how you need to do it. Is that okay? So the formula which is valid is N1 by N2 is V1 by V2. The formula which is not valid is N1 by N2 is I2 by I1. That is only valid if it is 100% efficient. Else you have to find the output power and then find the current. All right. All right, cool. Let's go. For an atom which has nucleus, nucleus is positively charged. The radius is very, very small. It's in femtometers. The radius of the atom by a factor of 10 to the power 4, more than 99% of the mass is concentrated at the nucleus. That is what even Rutherford said. Most of the atom is empty. Most of the 99% of the mass is just concentrated at the center of the atom, and that is where the nucleus is, and it is positively charged. And there are also some particles which are neutrons. On atomic scale, mass is measured in AMU. Basically, that is a small unit of mass, which is 1.66 10 to the power minus 27 kg, which is 1/12 the weight of a C12 isotope. Carbon 12, yes. Nucleus is neutral particle, contains a neutral particle called neutron. Its mass is almost same as proton. Yeah. So nucleus is not just positive; it is also made of neutral charges. The neutral particles are basically called as neutrons. Name also makes sense. Mass of a proton and mass of a neutron is almost same. Some people, I have heard them saying, sir, neutron is nothing but a proton and an electron marry each other, and that couple is called as a neutron because positive and negative will cancel. That is completely false. Please don't believe such things. Okay, that's not true. It's a new particle altogether. Atomic number Z is the number of protons, correct? The atomic mass number is protons and the neutrons. Mass number is proton and neutron together. Atomic number, which decides the chemical property, is only dependent on the protons in it, which decides the element, hydrogen, helium, lithium, etc. A nuclear species of nuclide is represented as AXZ. A is the atomic mass number, Z is the protons, X is the name of the element like helium, etc. When the atomic number is same, then it is called isotope. When the atomic mass number is same, it is called isobars. When the neutrons are same, it is called isotones. A nucleus can be considered to be spherical in shape and assigned a radius. So actually speaking, a nucleus is not exactly spherical, but you can almost take it like spherical. It's very small in femtometers, and the radius of such a nucleus is r0 a raised to 1 by 3. That constant is 1.2 fm. F stands for 10 to the power minus 15. Like you have milli, micro, then nano, then pico, then you have femto. Femto is minus 15. And remember, even if you take a big nucleus, heavy nucleus, matter, atomic mass number is huge, radius is huge, volume is huge, don't think the density is more or less. In fact, it is same for all the nucleus. If we divide the mass with the volume, all of them have the same density, which is 10 to the power 17 kg per meter cube, which is extremely huge. Neutrons and protons are bound in a nucleus by nuclear force. Obviously, think, how can a proton attract a neutron? It can't be gravity because mass is very less. It can't be electric because neutron doesn't even have a charge. So there is something which is new, and that is nuclear force. It's very short range within the nucleus. It has new properties altogether. It can be between proton and proton, neutron and neutron, neutron and proton. It doesn't depend on the mass, doesn't depend on the charge. It depends on the spin of the particles actually. Okay. Then this nuclear force is what holds these atoms, these nuclear particles together. And when these particles come together, then they release some energy. And Einstein said when energy is released, mass has to be destroyed. If energy is destroyed, mass has to be created. That is the principle of mass energy equivalence. Mass creates energy, energy can create mass, vice versa. So E is equal to mc square was the formula. M is the mass destroyed or created, E is the energy which is created or destroyed. So when these neutrons and protons assemble together inside the nucleus, the mass of the nucleus becomes slightly small. That difference of the mass is called as the mass defect. This is the mass of the protons, this is the mass of the neutrons. Subtract it with the mass of the nucleus, you get the mass defect. Substitute it here, you get the energy which is released. That energy which is released to bring them together, to bind them together, is the binding energy. Binding energy to form a nucleus. And when you calculate that binding energy per nuclear particle, that means the total protons and neutrons which are there, you divide it among them. If there are 70 protons and neutrons together, per proton and neutron, how much energy was released? That is called binding energy per nucleon. And this decides the stability. Binding energy per nucleon decides the stability. There is a beautiful graph which goes up and comes down. Iron is the most stable because it has more energy which is released per nuclear particle. More the energy released, it becomes very satisfied and very stable. When you talk about the energies with nuclear processes are about million times larger than the chemical processes, yes, makes sense because they are nuclear forces extremely strong, very short range. Q value of a reaction or a process, nuclear process, is the final energy minus initial kinetic energy. It is also initial mass minus final mass into c square. Radioactivity is the phenomena by which a nuclear particle disintegrates, giving alpha, beta and gamma. Alpha is doubly ionized helium, beta is electron, gamma is nothing but like X-rays. Okay, X-rays or infrared, it's an electromagnetic ray, it is not exactly a particle. Okay, energy which is going to come out in a less tightly bound nucleus are transmuted into more tightly bound nucleus. In fission, a heavy nucleus breaks into smaller fragments. Okay, so this is your nuclear fission reaction example which you should know. In fact, you can write it up as an example in your theory or paper, right? Uranium when bombarded with a neutron, you can see it is basically getting converted into a smaller daughter nucleus, one neutron is also released and another element is also created. So energy is released when a less tightly bound nucleus are transmuted, that means it is bombarded into more tightly bound nuclei. In fission, a heavy nucleus breaks into these smaller fragments, and this neutron goes and hits another uranium, and that breaks into more smaller elements, and a chain reaction occurs. In fusion, light nuclei combine to form a big nucleus. Fusion of hydrogen into helium, that is what occurs in the sun and produces tremendous amount of energy. Fuse means binding together. Hydrogen bringing together, forming helium. This was very important point. Density of nucleus is not going to be dependent. Density of nucleus is independent of the atomic mass number. Yes, keep this point in mind. 10 to the power 17 is the order. Radius of a nucleus is found by scattering experiment. This is not important. Einstein showed the equivalence of mass energy. The most convincing evidence is that the principle operates of nuclear physics is central to our understanding. This is also not important. Ignore. The nature of the binding energy curve shows that exothermic nuclear reactions are possible when two light nuclear fuse or when heavy nucleus undergoes fission into. Okay. So basically the nature, this 4th point, where the curve of binding energy per nucleon, the graph starts from hydrogen, where the value of B plus per nucleon is very small. Then it goes up, becomes the highest at iron, and then it starts dropping down till uranium, thorium. This graph shows that, some nucleus are not so stable. They want to be stable, and that comes by looking at the graph of stability of binding energy per nucleon. So nucleus like hydrogen, etc., they want to combine together and become a more stable nucleus. Heavy nucleus want to disintegrate. They're like, why do I want to become so heavy? Let me lose on some weight and become more stable like how iron is. So it explains why fission and fusion occurs. Although the binding energy nucleon curve is smooth and slowly varying, it shows peaks at nucleids like this thing. This is considered as evidence of atoms like shell-like structure in nuclei. So basically it says that just like atoms have orbits of electrons, even the nucleus has suborbits of these protons and neutrons. So don't think protons and neutrons are sticking to each other nicely happy. There are orbits even inside the nucleus, which probably explains why that curve is not so smooth, why there are sudden jumps up and down. Okay, just like how atomic spectra had discrete lines of atomic spectra, maybe that is a subtle hint that there are some shells even inside the nucleus. Electrons and positron are a particular antiparticle pair. Okay, they are identical. Okay, so positron, you might have heard of the word. Positron is like the twin brother of electron, same mass, same looking, identical, but instead of negative charge, it has positive charge. It's called as an antiparticle. So when there is good, there is evil. When there is sadness, there is happiness. So you see that always things go pair in pair. Always in the universe, you always find some kind of pairs which are there in almost all the things around you. Like you have husband, you have wife, you have love, you have hate, you have birth, you have death. So all things come in pairs. So same way, electrons also have a pair which is called as positron. All right. Radioactivity is an indication of instability of the nuclei. Okay. Now basically this point talks about radioactivity. Why do you think the particles of nucleus just split apart and become smaller stable nucleus? Because when the nucleus is heavy, when the binding energy per nucleon is not so great, they want to become more stable by achieving higher stability by releasing more energy, and that is explained, or that is proved by radioactivity. Or else there was no reason why a nucleus which is so strongly held by nuclear force should split apart. Okay, so that is an indication of the instability of the nucleus. That is the main point over here, right? That was in nucleus, right? Moving on to 206, full of energy, guys. Shall we go? Yes or no? Let me see some red hearts in the chat box here. Quickly. Full of energy, full of juice. Have you guys smashed the like button already? No, if you have not, please do that. Yeah, support the channel. And I want every one of you attending the session to smash not just the like button, but also comment after the video and share this video with your friends, with your community. Yep. Thank you, Ram, for increasing the Josh. Krishna, thank you so much. Thank you, Srinath. Thank you, Samira. Thank you, yaar. Thank you so much. I need this energy. I need this energy. Where is Pandu? Victor, Pandu is attending the class. Pandu is studying. Pandu is like, sir, I will come when students are little bit chill. Today's students are very tensed. Today's students are very nervous. Today's students are very demotivated for some or the other reason. Today's students are getting scared of tomorrow's exam. Okay, so my dear students, there is no need to worry. Board exams, especially the physics one, I am pretty sure it will not be very tough. And whatever things you have been doing in the last 5 days, 6 days, if you have been part of this particular challenge, this will be very, very, very fruitful in tomorrow's exam, and you will see why. Okay, many things will get repeated, many things you will find it to be very familiar, hidden lines, hidden pointers. We have covered almost everything, all the chapters we are doing in a very hidden manner, because you might read NCERT again and again, many things you might skip. Derivations you might have skipped, graphs you might have skipped, problems you might have not solved much. So we have done all these things. It's like a 360-degree coverage of the studies what is required for your board exam. And yes, it's going to be definitely helpful for your upcoming NEET and JEE examination. Just think about it. After this, we start with the 11th standard backlog classes. What say? Won't you want it? 11th standard, some chapters we have already done in the series. So the remaining chapters, let's say we start covering it up, you know, as backlog express or whatever you want to call it. And we finish the series where we started off, you know, 2 months back. And we cover as many chapters as possible in the next 2 weeks. You'll be thoroughly prepared, even with the 11th standard portion. Wouldn't you want that? Yeah. So that's the reason why I keep asking you to subscribe to the channel, because your journey is not going to end tomorrow or day after tomorrow. It's going to continue even after that, because there are a lot of exams that we need to prepare for, right? So stay tuned. Thank you for subscribing and thank you for liking the video as well. Coming on to semiconductors, the final chapter, full of josh, full of energy. Thank you to your thank you for your chat box being lighted up with those smileys, with those emojis, with those fire symbols and those heart symbols. Thank you so much. Okay, semiconductors are the basic materials used in the present solid state electronic devices like diode, transistor, ICs. Semiconductors are somewhere between conductors and insulators. They have very unique properties when you compare it with conductors or insulators, and they are in solid state, meaning it's not generally used in gas form or in liquid form or in electrolytic form. It's in solid state devices like integrated circuits, diodes and transistors. You will find these components in almost each and every electrical device or appliance around you. The lattice structure and the atomic structure of the elements decide whether it is insulator, metal or semiconductor. So yes, how it is arranged, how the electrons are configured, what is the energy, what is the gap of the energy, how they mingle with each other, decide the material type. Metals have very low resistivity. Insulators have very high resistivity. Semiconductors are somewhere in between. Typically, these are the values. Semiconductor elements like silicon, germanium, or even compounds like cadmium sulfide, right? GAAS. All these are semiconductor materials. Don't think only elements, pure elements, but even compounds can be semiconductors like GAS and CDS. Pure semiconductors which are not adulterated by or influenced by other doped materials, they are intrinsic semiconductors, internally pure, intrinsic. The presence of charge carriers like electrons and holes is an intrinsic property of a material, and they are obtained as a result of thermal excitation. Ne is electron concentration, NH is hole concentration. Holes are basically electron vacancies, which is effectively a positive charge. Meaning, when you take an intrinsic semiconductor like GAS or silicon or germanium, you will see that there is a small set of electrons which jump, which get excited into the conduction band. The band gap, which is the energy difference from valence to the conduction band, is typically 1 or 2 electron volt, which makes it very easy for the electrons to jump into the conduction band with decent amount of thermal energies due to the collision. Okay, the electrons get knocked out into the conduction band. Now what happens is, because of this jumping, these electrons are moving everywhere around in that solid or that crystal. So when an electron leaves, it creates a vacancy called as a hole. That is nothing but a positive charge effectively, and the electron is also moving somewhere. This hole will probably get filled up by some other electron coming from some other place. So this hole will migrate now, this vacancy will migrate now to a new place. So it's as if the positive charge has migrated to some other place, so positive charge will flow. Same time, electron is going somewhere, so there is also basically electron flow which is happening, negative flow which is happening. So there are both kinds of carriers, electron which is negatively charged and holes which is positively charged in a semiconductor. This is one very unique difference when you compare it with conductors, where you do not have positive charges moving, you just have electrons moving. Next, when you talk about the number of charge carriers and can be changed by doping, that is called as extrinsic or impure semiconductor. They are of two types, P and N. Usually in an intrinsic semiconductor, amount of holes, vacancies, and the amount of negatives, which is electrons, are equal. NH and Ne are equal. But when holes are more vacancies and less electrons, it becomes P type of semiconductor. When electrons are more, holes are less, it becomes N type of semiconductor. Please mind that P and N type are not positive or negatively charged. They both are electrically neutral. Okay, don't think so N type material means more negative charge, so it is negative, right? No. Yeah, it has excess electrons because of that external element, maybe like phosphorus. But don't forget, the phosphorus atom also has an excess proton in the nucleus, which keeps it neutral. So understand, P and N type actually technically are electrically neutral. Okay, this relationship is always true. Number of electrons into number of holes per unit volume is Ni square. What is Ni? Is the hole or the electron concentration. For I stands for intrinsic semiconductor. So when you have P type, NH is more, Ne is less. When you have N type, Ne is more, NH is less, but their product remains constant, which is Ni square. There are two distinct band of energies called as valence band and conduction band, in which the electrons in a material lie. Valence band energies are low as compared to the conduction band energies. Yes, like I told you, there are two different bands of energies. Like you have K shell, L shell, M shell, etc. in an atom. But for a crystal lattice structure or a solid structure, it's not those shells, you have bands, and the valence band is where the electrons completely occupy those energy levels. That's a valence band. Conduction band is not completely occupied, and conduction band is where if an electron is present, can be easily accommodated or can be easily used for conduction of electricity. And the difference of the energy between them, valence and conduction, is used for calculating band gap. For insulators, band gap is huge. For semiconductors, it is very small, so easily electrons can jump with decent excitation. And for conductors, it overlaps, so you don't have to do anything, automatically they can enter into the conduction band. Okay, next. So I have mentioned those energy band gaps. I just told you about the energy band gap. For insulators, it's more than 3 electron volt. For semiconductors, it is hardly anything. For metals, or conductors, it is overlapping. So there is no band gap only. Now the PN junction is the key to many semiconductor devices. Such a junction is made with a depletion layer with immobile blah blah blah. This is responsible junction potential barrier. So remember, in a PN junction, P and N, P is hole, N is electrons. The moment electrons see holes, they will immediately jump, tuck, 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 tuck. That jump which happens is called as diffusion. Like you might have heard of diffusion of gases in chemistry. If hydrogen gas is there here, helium gas is there here, and there is a chamber here and there is some membrane or some wall in between, you remove the wall, the gases diffuse, they mix, spread. Same way here also, P and N, P has positive, N has negative, you remove or you join them, you remove the barrier between them, that's it. Immediately they start diffusing. So electrons will jump into the P side, and the holes which are there, they will be accommodating those electrons. So that is called as diffusion process. The current which is produced is called as diffusion current. Please remember, current is always in the direction of positive charges. So it will be opposite to the flow of the electrons. So if electrons go from N to P, diffusion current will go from P to N. That is another thing to keep in mind. Because of this jump, P becomes negatively charged, N becomes positively charged. So because of the charge difference, there is a voltage difference, there is electric field between them, and that voltage difference is called as a barrier, potential barrier. And this barrier is like a wall which prevents more electrons or holes from jumping here to there. There is a simultaneous current which is in the opposite side, which happens because of thermal collisions, and that is from N to P, not from P to N. N to P, it's exactly opposite. It is called as the drift current. It is purely dependent on the material and the temperature. When you have unbiased PN junction, both diffusion and drift are equal. When it is forward bias, diffusion is more, drift is less, or as it is. But when it is reverse bias, diffusion decreases. So majorly drift is there, and that is negligible. So very small current flows in the circuit, often called as the leakage current. Leakage current, which is in reverse bias, it is negligible. In forward bias, the moment you apply forward bias voltage, the diffusion current increases, and the moment the barrier breaks, remember that potential barrier was there, the barrier shuts down, that's it, there is a sudden surge of current, and you will see a non-linear increase of the current with the applied voltage. That is also given in the current versus voltage graph, which is also there in your textbook, which looks like this. It goes up. I have discussed that in the graph. Okay, so you should know both the biases, forward, reverse bias, and the 4 main applications of diodes. One is LED, light emitting diode with the symbol. It is used in forward bias. Then you have photodiode with the symbol you should know. It is used in reverse bias to detect the light, and the light affects the conductivity. Third is solar cell, you should know, right? The solar cell, right, everyone? And then last one, you should also know rectification and rectifier process. Both types of rectifiers, half wave and full wave. Half wave and full wave. And also the use of capacitors in a rectifier to filter out the ripples, to remove the ripples. Keep that in mind. Okay, all these things are very, very important. Okay, let's look at points to pointer. The energy bands EC or EV in the semiconductor are space delocalized, which means these are not located in a place. They are overall averages. When you see a picture of EC or EV are drawn in straight lines, they should also be respectively taken simply at the bottom of the conduction band energy levels and the top of the valence band energy levels. Okay, so remember, when you draw energy levels in an atom, there are lines, but that's for an atom. But for a solid structure, those are not lines, those are range of values. A range of values, that's why it is called as a band. Valence band energy, conduction band energy. So when I say EC, EV, energy of conduction band, energy of valence band, which energy am I referring to? Because it's a band, it's a range. So usually we refer to the highest valence band energy in that range, because valence band has lower energy, highest valence band energy. And for conduction, we take the lowest conduction band energy. So from conduction, we take the lowest value. From valence, we take the highest value. So the difference of these two gives you the band gap. Okay. Next, in an elemental semiconductor like silicon, germanium, N and P type are obtained by dopants or defects. Remember, you say that you introduce some impurity. When you add a trivalent impurity, then you make a vacancy, you create a vacancy, create a hole. Holes are in excess, it makes it P type. When you add pentavalent impurity, you add one excess electron, N type semiconductor. These materials are called as dopants or defects, which makes it extrinsic semiconductor. There might be relative change in the stoichiometric ratio, can also change. For example, in an ideal GAAS, the ratio of GA is to AS is 1:1, but in GA rich or AS rich, GAS, it could be respectively GA 1.1, AS 1. Generally, the presence of defects control the properties in many ways. Okay, so see, when you have an elemental semiconductor, means the semiconductor is made of elemental atoms like silicon or germanium, then the doping is slightly in different ratio. But when you talk about compound based semiconductor like GS or CDS, the cadmium sulfide, there the dopants that you add depends on what percentage of individual elements are present in that particular compound. That's what it says, but you don't have to break your head over it. It's just mentioned for the sake of it. Nobody can ask you a question on this. It is meaningless, right? So that was semiconductors. Yeah, that's the end of it, I believe. Yep. Yeah, we have done all of this. So now what are you going to do after this? We are going to, please go through your NCERT. You might have realized so many things you know or don't know. Whatever things you don't know, just try to see those things. But if there is a chapter which you have not done, please don't do that. It's okay. Whatever chapter you have done, in that, whatever you don't know, just do that much. Okay? Number 2, don't get tensed. Everything will be fine tomorrow. It's not going to be very difficult. It is board exam. It is not JEE advanced exam or Olympiad exam or some very difficult AIMS level paper. No, it is a board exam. Number 3, keep a track of your time. I have been telling you this again and again. See the mock test. See the pattern of the questions. You will always be given a choice. Make the best choice so that you don't waste time. Aim should be to maximize the marks. Keep a track of your handwriting, your order of solving. Don't miss any question. Okay, in the question paper, make sure you are tick marking everything and solving everything. Don't solve unnecessary options, like it says you can solve A or B. You solve both A and B. Don't do that. If it is given as an option, either you do this or do that. You won't get marks for both. Okay, so keep a track of time. Be very legible. Don't do too many cancellations. Do proper rough work. I think everything should be sorted. Okay, just go confidently and please sleep early. For those of you who are legends or ultra legends and need some special help, I'll try to take a class at 4 o'clock. okay, and see what we can do. I'm not yet sure what we should do, but we'll do something. Okay, thank you so much. Thank you for joining in. We'll see you guys soon. And yeah, the 11th standard bachelor classes, or basically 11th standard classes, will also continue. Whatever chapters we have done, we'll not do that again. We'll not waste time there. Whatever we have not done, we'll try to complete those. Okay, thank you. Bye bye. All the best. Captain Shreyas signing off. Hasta la vista.